The Ultimate Kubernetes Platform Engineer Masterclass, 218 Real-World Production Incidents.
In the modern enterprise, the role of a Kubernetes platform engineer is the thin line between stable uptime and complete operational collapse. This masterclass is a deep dive into the raw, unedited war stories of high-scale systems, 218 real-world production incidents, platform failures, and architectural emergencies. This series is designed to prepare you for the highest levels of technical interviews and day-to-day production pressures, equipping you with the forensic mindset needed to protect the infrastructure that runs the world's code.
The two-part series roadmap, navigating 218 production incidents.
Guarantee absolute mastery of both the low-level technical engine and high-scale operational strategy. We have divided this masterclass into two comprehensive parts. Part 1. The core engine and infrastructure production incidents 1 to 103 deep dives into Kubernetes control plane stability, worker node and OS internals, pod lifecycle, high-performance networking, and stateful storage. Part 2. Enterprise operations, scale, and security production incidents 104 to 218, focusing on GitOps pipelines, complex autoscaling, observability bottlenecks, cloud platform limits, service meshes, and disaster recovery. Part 1 establishes the infrastructure foundation. Part 2 secures the enterprise scale. Let's begin with Part 1.
Part 1. The core engine and infrastructure.
In this first video, we dismantle the inner workings of the Kubernetes engine. We will walk through 103 production incidents, testing the absolute limits of the control plane, worker nodes, operating systems, and network paths. We will analyze exactly what happens when native boundaries break under load, and how you as a platform engineer can re-architect the system for survival.
Part 1. Domains of infrastructure mastery.
We will master the following 5 critical domains in this first volume. Category 1. Kubernetes control plane incidents production incidents 1 to 20. Category 2. Worker node and OS level incidents production incidents 21 to 40. Category 3. Pod and workload lifecycle incidents production incidents 41 to 60. Category 4. Kubernetes networking incidents production incidents 61 to 88. Category 5. Storage and stateful platform incidents production incidents 89 to 103. 103 high-severity production incidents ahead. Let's dive straight into Category 1.
Category 1. Kubernetes control plane incidents.
The Kubernetes control plane is the nervous system of your entire cluster. If the API server lags, or etcd loses quorum, the entire ecosystem immediately paralyzes. This category is a forensic exploration of control plane collapse, from watch cache memory explosions to webhook deadlocks and etcd wall corruptions. We will test your ability to diagnose and stabilize the core administrative layer under massive operational pressure.
Category 1. Control plane production incidents 1 to 20.
Here are the 20 production incidents covering control plane failures. Production Incident 1. Kube API server crash looping after certificate expiration. Production Incident 2. API server unavailable due to etcd quorum loss. Production Incident 3. Kube API server saturation during massive deployment storms. Production Incident 4. Admission webhook timeouts blocking cluster-wide deployments. Production Incident 5. Mutating webhook ordering conflicts crashing startup pods. Production Incident 6. Mutating admission webhook silent failures corrupting pod specs. Production Incident 7. Validating webhook failure policy. Fail taking down system pods. Production Incident 8. Excessive exec and port forward connections exhausting the API server. Production Incident 9. KMS encryption plugin downtime breaking secret decryption. Production Incident 10. etcd wall corruption causing cluster instability. Production Incident 11. etcd database quota exceeded due to neglected defragmentation. Production Incident 12. Kube API server watch cache from large secrets and config maps. Production Incident 13. Aggregated API server failures breaking kubectl operations. Production Incident 14. API priority and fairness misconfiguration starving critical requests. Production Incident 15. Scheduler unable to place pods due to resource fragmentation. Production Incident 16. Controller manager or scheduler leader election flapping. Production Incident 17. Cluster upgrade failed due to deprecated APIs or version skew. Production Incident 18. CRD conversion webhook failures during upgrades. Production Incident 19. Massive CRD growth slowing Kubernetes API performance. Production Incident 20. Control plane instability during massive cluster events. Total 20 production incidents for the control plane. Let's start with Production Incident 1.
Production Incident 1. During a scheduled cluster maintenance window, the primary control plane node's Kube API server enters a continuous crash loop backoff state, rendering the Kubernetes API completely unresponsive. Internal monitoring alerts indicate that the root cause is the expiration of the client certificate used for PI server to kubelet communication. With the kubectl CLI completely paralyzed, what is your containment and remediation strategy?
Answer: this is an administrative lockout caused by PKI infrastructure expiration. I would handle this via a direct node-level recovery plan. 1. Bypass the API. SSH directly into the master control plane node using root privileges to bypass the broken API server and access the underlying file system directories directly. 2. Assess certificate expiration. Navigate to /etc/kubernetes/pki and execute diagnostic commands directly against the local open SSL binaries to identify exactly which certificates are expired. 3. Manually force renewal. Execute local static configuration commands via the kubectl utility on the host system to force a manual renewal of the expired control plane certificates. 4. Restart the static pods. Move the static pod manifests out of /etc/kubernetes/manifests and back in to force the local kubelet to recreate the kube API server static container with the new certificates. Pro tip: do not wait for manual alerts to catch certificate expirations. Implement Prometheus monitoring rules targeting the API server _certificate_expiration_seconds metric to trigger high-severity alerts at the 30-day and 7-day mark, allowing automated workflows to renew them via your platform engine pipeline. Here is Bash configuration, demonstrating how to check and renew Kubernetes control plane certificates to prevent API server crash loops. Disclaimer: always test code in a non-production environment. Here is the code checking the expiration status of all static pod certificates to locate the specific expired client key. This code executes the manual renewal of the API server client certificate to restore secure communication to the control plane.
Production Incident 2. During a sudden network partition between availability zones, 2 out of 3 control plane nodes lose connectivity, resulting in immediate etcd quorum loss. The active Kube API server instances immediately stop serving requests, throwing 500 internal server errors and causing cluster-wide deployments to halt. What is your troubleshooting approach to safely restore etcd quorum without risking data split brain?
Answer: this is an etcd replication failure caused by network partitioning. First, I would check the cloud provider console to verify if the underlying network partition is healed, preventing a potential split brain scenario. Next, I would SSH into the remaining healthy control plane node, locate the etcd static pod manifest at /etc/kubernetes/manifests/etcd.yaml and modify the startup flags to temporarily run etcd as a single node cluster using the --force new cluster flag. Once the single node control plane is stable and accepting API rights, I would sequentially rejoin the other partition members as clean nodes, allowing them to rebuild their databases sequentially from the master node. Pro tip: never attempt to manually merge partitioned etcd databases. If you lose quorum, always choose a single authoritative node to force, initialize a new cluster, then clean the directories and resync the remaining members one by one to ensure transactional integrity.
Production Incident 3. During a major marketing campaign release, an automated CI and CD pipeline triggers a deployment storm of 5,000 parallel microservice updates, while simultaneously, several platform operators perform rapid CRD status writes. The Kube API server CPU spikes to 100%, causing webhook timeouts and massive 4292 mini request errors that paralyze all admin operations. What is your containment and remediation strategy?
Answer: this is an API saturation crisis caused by high concurrency writes. I would stabilize the control plane using these steps. 1. Isolate CI and CD traffic. Configure a standard API priority and fairness APF policy targeting the service account used by the CI and CD pipeline to restrict its maximum concurrency levels. 2. Enforce rate limiting. Apply an active flow schema to dynamically redirect aggressive deployment traffic to a low-priority queue with a concurrency limit of 50 concurrent requests. 3. Verify handshake capacity. Scale up the underlying master node VM resources or increase the --max mutating requests in flight configuration flag inside the API server static manifest. 4. Audit watch cache size. Verify that the watch cache sizes on highly populated custom resources are not exhausted, preventing extensive etcd database sweeps. Pro tip: default Kubernetes clusters have very permissive write limits. Always isolate your deployment engines and custom platform operators into designated APF flow schemas with highly restricted concurrent execution ceilings. This ensures your human platform engineers can always run diagnostic commands during deployment storms. Here is Kubernetes configuration demonstrating how to configure flow schema and priority level configuration to protect the API server from scaling storms. Disclaimer: always test code in a non-production environment. This code configures the mapping of incoming client requests to a specific administrative bucket, preventing aggressive pipelines from starving system operations. Here is the code applying the rate limit individually by user rather than globally, guaranteeing that one malfunctioning controller cannot consume the entire resource budget of the API server.
Production Incident 4. An enterprise-wide security admission webhook experiences a silent network partition and begins timing out on all resource validation requests. Because the webhook's failure policy is set to fail, all deployment, pod creation, and update requests across the entire production cluster are blocked, freezing the delivery pipeline. What is your containment and remediation strategy?
Answer: this is an admission validation deadlock. I would immediately SSH into a master node, bypass standard API validation by using a localized administrative kubeconfig that accesses the API server directly, and execute an emergency patch on the validating webhook configuration object. I would temporarily change the failure policy flag from fail to ignore and reduce the timeout seconds limit to 2 seconds, which allows deployment traffic to flow smoothly without waiting for the network partition to heal. Once traffic is unblocked, the team can perform a rolling restart of the security webhook deployment pods in the target security namespace. Pro tip: never configure any critical validating or mutating webhook with failure policy. Fail unless you have explicit, redundant, multi-zone deployments of your webhook servers. Always define strict timeout seconds values 2 to 3 seconds maximum to ensure that even during network latency spikes, your cluster-wide API operations do not lock up indefinitely.
Production Incident 5. A high-priority application pod fails to start because the HashiCorp Vault Agent sidecar was injected after the Istio Envoy sidecar, preventing the Envoy proxy from accessing the necessary decrypted TLS certificates on startup. The pod gets stuck in an it: crash loop backoff because of this mutating webhook race condition. What is your containment and remediation strategy?
Answer: this is a webhook execution sequence conflict. I would re-architect the mutation lifecycle through these operations. 1. Enforce reinvocation heuristics. Modify the mutating webhook configuration for the Vault Agent injector to set the reinvocation policy field to reinvoke if needed. 2. Differentiate priority levels. Explicitly order the mutation phases by adjusting the webhook names alphabetically, as the API server executes webhooks in lexical order within each phase. 3. Migrate to native sidecars. Transition the sidecar container definitions to utilize the native init container restart policy, always feature introduced in modern Kubernetes. 4. Audit controller loops. Review the container start sequence inside the pod manifest to ensure the initialization steps explicitly wait for the Vault sidecar to mount secrets. Pro tip: mutating webhooks do not inherently execute in a predictable sequence. Always leverage the reinvocation policy. Reinvoke if needed flag to force previously executed webhooks to evaluate the pod spec again, if a subsequent webhook like Istio appends new sidecars or volumes. Here is Kubernetes configuration, demonstrating how to set reinvocation policy on mutating webhooks to prevent sidecar injection ordering conflicts. Disclaimer: always test code in a non-production environment. This code sets the reinvocation policy to force the API server to execute the mutating webhook a second time if a subsequent webhook modifies the pod spec.
Production Incident 6. A custom internal mutating webhook begins executing silent, buggy JSON patches on incoming deployment specs, corrupting the container argument lists without returning any explicit admission errors. Platform teams only detect the corruption when downstream workloads start failing silently at runtime due to misconfigured start commands. What is your troubleshooting approach?
Answer: this is an unmonitored mutation corruption. I would immediately review the Kubernetes audit logs to track down the exact mutations applied to the deployment resource, filtering audit events by the webhook's request URI, and analyzing the response object payload to isolate the mutated fields. Next, I would patch the webhook service, forcing it to write diagnostic details into a structured event within the target namespace to provide instant visibility into mutated pods. For a permanent fix, I would configure linting rules in the mutating webhook server to validate output patches against the original schema, and implement an audit-only webhook pipeline that flags non-compliant mutations before they write to the etcd storage layer. Pro tip: mutating webhooks should always write an admission event back to the resource they modified. This provides an audit trail directly within the kubectl describe output, allowing developers to instantly identify if an infrastructure webhook altered their configuration.
Production Incident 7. A platform engineer deploys a strict Kyverno validating policy aimed at enforcing resource limits, but the validating webhook's failure policy is set to fail. When the webhook server becomes briefly overloaded, it begins rejecting all pod creation requests, including critical core DNS and CNI daemon set pods, triggering a cascading network collapse across the entire cluster. What is your containment and remediation strategy?
Answer: this is a webhook feedback loop locking up system pods. I would isolate the control plane using these steps. 1. Exempt infrastructure namespaces. Modify the Kyverno validating webhook configuration to add a strict namespace selector that explicitly excludes kubesystem and other administrative namespaces. 2. Bypass critical operations. Reconfigure the admission rules to only intercept user-facing workloads, preventing the webhook from intercepting system daemon set operations. 3. Implement horizontal scaling. Increase the webhook deployment replica count to 3, establishing anti-affinity rules to distribute the instances across healthy master zones. 4. Gracefully degrade policy. Reconfigure the webhook configurations to utilize the failure policy. Ignore directive until comprehensive health monitors are established. Pro tip: never let admission webhooks intercept the kubesystem namespace. Always configure your validating webhook configuration with a strict namespace selector exclusion to prevent system components like DNS and network plugins from getting trapped in webhook failure cycles during cluster-wide emergencies. Here is Kubernetes configuration, demonstrating how to configure namespace selector exclusions on validating webhooks to protect system pods. Disclaimer: always test code in a non-production environment. This code configures namespace selectors that explicitly exclude administrative namespaces, preventing critical system pods from being intercepted by validation logic.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 8. An internal developer portal misconfiguration triggers continuous, unclosed stream connections using exec, port forward, and logs APIs against hundreds of production pods. The Kube API server reaches its maximum concurrent connection limit, causing the control plane to stop responding to standard kubelet heartbeats and triggering false node evictions. What is your troubleshooting approach?
Answer: this is an API stream exhaustion crash. I would first identify the source IP addresses of the aggressive streaming requests by analyzing the active TCP connections on the control plane host using the SS or netstat utility tools. Next, I would configure temporary firewall rules at the load balancer level to block the portal's IP address, freeing up concurrent connections immediately. I would then update the API server configuration manifest /etc/kubernetes/manifest/kube API server.yaml to adjust the --max requests in flight and --max mutating requests in flight boundaries to ensure administrative traffic is safeguarded. To prevent a recurrence, I would configure strict keep alive timeouts and enforce automatic connection closures for all stream operations. Pro tip: long-running connections like exec and port forward bypass standard API timeouts. Always configure your API servers behind a reverse proxy like Nginx or HA proxy that enforces connection limits and connection duration timeouts for /API/v1/namespaces//pods/exec endpoints.
Production Incident 9. The external cloud KMS provider used for encrypting Kubernetes secrets at rest experiences a regional outage, causing the KMS plugin on the control plane to time out. Consequently, the Kube API server is unable to decrypt secrets, preventing new pods from booting up and breaking all active service account token rotations. What is your containment and remediation strategy?
Answer: this is a decryption plugin dependency failure. I would restore secrets functionality using these steps. 1. Evaluate cache configuration. Inspect the /etc/kubernetes/encryption config.yaml file to verify if the KMS provider is utilizing the modern v2 API with local key caching. 2. Temporarily append plaintext fallback. Add the identity empty braces fallback provider directly below the KMS provider configuration in the encryption configuration file. 3. Trigger API manifest reload. Save the configuration changes, which forces the Kube API server static pod to automatically reload and re-establish write functionality for new records. 4. Audit secret writes. Ensure that any secrets created during this emergency recovery period are flagged for automatic re-encryption once the cloud KMS provider is restored. Pro tip: standard KMS v1 configurations require a network round trip for every single secret read. Always migrate to the KMS v2 configuration, which supports a secure cache size parameter, enabling the API server to decrypt the data encryption key once and cache it safely in memory to survive cloud outages. Here is Kubernetes configuration demonstrating how to configure KMS v2 encryption providers with local caching to maintain secret decryption capabilities during cloud outages. Disclaimer: always test code in a non-production environment. This code defines the local key cache size, directing the API server to store decrypted data encryption keys in memory, and avoid external KMS network round trips during cloud outages. Here is the code specifying the plaintext fallback provider, ensuring the API server can continue executing emergency write operations if the KMS plugin remains unresponsive.
Production Incident 10. Following a sudden physical power loss on a control plane bare metal node, the primary etcd member fails to start, with the logs displaying a critical write-ahead log wall corruption error. The rest of the etcd cluster is experiencing extreme replication lag and data inconsistency, threatening the integrity of the cluster state. What is your containment and remediation strategy?
Answer: this is a local etcd storage corruption event. I would immediately isolate the corrupted node by removing it from the active etcd membership pool using etcd member remove on a healthy node to prevent corruption from spreading. Next, I would SSH into the broken node, stop the local etcd static pod, and completely delete the corrupted data directory located at /var/lib/etcd/member. I would then re-add the node as a clean member on a healthy node via etcd member add, and restart the local etcd container on the corrupted node. The newly added member will automatically connect to the active leader, download the database snapshot, and rebuild its wall cleanly from scratch. Pro tip: always maintain an external automated cron job that takes hourly etcd snapshots using etcd snapshot save and pushes them to secure S3 storage. If you experience massive wall corruption across multiple nodes, restoring from a clean snapshot to a new data directory is your only guaranteed recovery path.
Production Incident 11. During a massive automated rollout, the entire Kubernetes control plane suddenly stops accepting write operations, and the Kube API server logs indicate that etcd has reached its hard-coded database space quota. The cluster is paralyzed, throwing etcd server. MVCC. Database space exceeded errors across all nodes. What is your containment and remediation strategy?
Answer: this is an etcd keyspace limit crisis caused by uncompacted revisions. I would stabilize the database using these recovery steps. 1. Extract current revision. Query the current etcd store status directly via the etcd loopback command on the node to identify the latest logical cluster revision. 2. Execute logical compaction. Force a manual compaction of historical revisions up to the current revision to free up the logical keyspace. 3. Reclaim physical storage space. Trigger a physical defragmentation run across all etcd members sequentially to release unallocated disk blocks back to the host file system. 4. De-escalate cluster alarms. Reset the active etcd space quota alarm flag using the endpoint alarm disarm command to restore write functionality to the control plane. Pro tip: default etcd installations have a conservative 2 GB database limit. Always configure the -- quota backend bytes flag explicitly to 8 GB, the recommended maximum, and enable the automated -- auto compaction retention flag with a 5-minute window to prevent historical revision bloat from triggering hard shutdowns during deployment storms. Here is bash configuration, demonstrating how to compact and defragment the etcd database to recover from space quota exhaustion. Disclaimer: always test code in a non-production environment. This code executes the compaction of old MVCC historical revisions up to the latest revision, clearing the logical keyspace within the etcd database. Here is the code performing a physical defragmentation on the etcd storage, releasing the freed blocks back to the underlying operating system file system.
Production Incident 12. Following the accidental deployment of a third-party logging agent that mounts thousands of oversized, unencrypted secret, and config map objects, the primary Kube API server runs out of memory and crashes. JFR telemetry shows a watch cache memory explosion caused by the massive serialized footprints of these resources. How do you resolve this control plane memory exhaustion?
Answer: this is a control plane memory starvation incident caused by watch cache bloating. I would immediately SSH into the master node and modify the API server manifest /etc/kubernetes/manifest/kube API server.yaml to adjust the -- watch cache sizes flag, explicitly shrinking the cache allocation size for secrets and config maps to prevent further heap inflation during the startup phase. Once the API server is stabilized, I would implement a strict platform policy enforcing maximum sizes, for example, limit secrets to under 1 megabytes, and configure Kyverno policies to block the creation of oversized config maps. Lastly, I would refactor the client-side logging agent service account permissions, restricting it from executing wildcard watch operations on non-essential, large-scale resource types across the entire cluster. Pro tip: the Kube API server maintains an in-memory watch cache for every resource type by default. If your cluster scales to thousands of large secrets or config maps, use the -- watch cache sizes parameter to explicitly restrict memory-intensive caches, forcing clients to stream updates directly from etcd or rely on highly optimized informer-based filtering mechanisms.
Production Incident 13. A custom metric aggregated API server experiences a complete outage, causing all standard kubectl commands like kubectl get, kubectl describe, and autocomplete to hang for 30 seconds and ultimately fail cluster-wide. What is your troubleshooting approach to identify and isolate the faulty aggregated service?
Answer: this is an API registration routing failure. I would debug and detach the blocking endpoint using these steps. 1. Track down the API service. Run a diagnostic kubectl get API service command to inspect the availability status of all registered aggregated API endpoints. 2. Locate the blocked group. Filter the output to find API services showing a false status or displaying connection timeout errors. 3. Evaluate webhook connectivity. Inspect the core service and endpoint backing the faulty aggregated API to verify if target container pods are running and responding to handshakes. 4. Perform emergency deletion. Delete the misbehaving API service object entirely to immediately unblock the API server from routing requests to the dead endpoint. Pro tip: aggregated API servers act as unified extensions of the core API. If an aggregated endpoint is unresponsive, the API server hangs on discovery sweeps. Always configure custom API services with short timeout parameters and verify that your validation webhooks can bypass aggregation failures. Here is Kubernetes configuration demonstrating how to register an aggregated API service with failure protection to prevent cluster-wide kubectl hangs. Disclaimer: always test code in a non-production environment. This code specifies the base 64 encoded CA certificate used by the primary API server to validate the webhook's TLS handshake, preventing secure handshake failures from blocking aggregated requests.
Production Incident 14. An emergency API priority and fairness APF configuration change goes wrong, and a custom flow schema accidentally routes critical system requests, including kubelet status updates and leader election heartbeats, into a highly restricted, throttled queue. As a result, nodes begin flipping to not ready and system controllers stall. How do you recover and correct the prioritization engine?
Answer: this is a control plane starvation incident caused by misconfigured traffic routing policies. Since kubectl commands are likely timing out or severely delayed due to the bad APF rules, I would use an administrative local kubeconfig to bypass the public load balancer and connect directly to the master node's loopback API endpoint. I would immediately delete the misconfigured flow schema or manually edit the priority level configuration object to restore the default concurrency limits for the system queue. After restoring control plane stability, I would refactor the APF rules to ensure that system subjects, such as kube system service accounts and system nodes groups, are mapped exclusively to the exempt system nodes or leader election priority levels, which are hard-coded to bypass APF concurrency throttling entirely. Pro tip: never map critical system controllers or node groups to dynamic APF queues. Always leave the standard, out-of-the-box system nodes and leader election priority levels untouched, and verify that any new user-defined flow schemas have a low matching precedence value, for example, greater than 1,000, so they cannot override system-critical rules.
The universal interview tip: whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 15. Your production cluster has plenty of aggregate CPU and memory capacity, but a batch of high-priority application pods remains stuck in a pending state due to 0 or n nodes available. Insufficient CPU errors. Your investigation reveals extreme resource fragmentation, where tiny unused slivers of CPU are scattered across 200 nodes, but no single node has a contiguous block large enough to fit the new pods. What is your containment and remediation strategy?
Answer: this is a scheduling bottleneck caused by bin packing failure. I would defragment the cluster compute using these steps. 1. Identify fragmented nodes. Run a scheduling analysis script to map the specific allocation requests versus actual active limits across all worker nodes. 2. Enforce scheduler bin packing. Modify the scheduler policy configuration to prioritize the most allocated scoring strategy instead of the default least allocated strategy. 3. Define topology spread fallbacks. Configure the application deployments to utilize topology spread constraints with a relaxed satisfaction policy. 4. Trigger graceful rebalancing. Initiate a rolling drain of the most underutilized nodes to force existing workloads to pack tightly onto fewer, high-density host nodes. Pro tip: default Kubernetes schedulers try to spread workloads evenly, which inherently maximizes fragmentation. Always use tools like discheduler in high-scale environments to gracefully evict and relocate fragmented workloads, and define highly accurate container CPU requests to ensure the scheduler can compute optimal packing. Here is Kubernetes configuration, demonstrating how to use topology, spread constraints, and resource requests to prevent node-level resource fragmentation. Disclaimer: always test code in a non-production environment. This code sets the fallback scheduling heuristic to allow the scheduler to pack workloads onto fragmented nodes when strict zone or hostname spread requirements cannot be perfectly met.
Production Incident 16. During a period of intense networking jitter, the Kube Controller Manager and Kube Scheduler components experience continuous leader election flapping. The active instances repeatedly lose their leases and restart, causing deployments to stop reconciling and pods to get stuck in a pending state for minutes. What is your troubleshooting approach to stabilize leader lease locking?
Answer: this is a control plane split brain threat caused by transient network latency. I would first analyze the lease resources in the Kube system namespace to evaluate the frequency of lease transitions and identify the exact latency spikes. To mitigate the flapping immediately, I would modify the /etc/kubernetes/manifests/kubecontrollermanager.yaml and kubescheduler.yaml manifest to increase the lease duration thresholds, specifically tuning the -- lease duration to 30 seconds, -- renew deadline to 20 seconds, and -- retry period to 5 seconds. This provides a larger buffer for transient network latency, ensuring the current leader does not prematurely yield its lock during minor connection drops, while our network team troubleshoots the underlying switch packet losses. Pro tip: tuning leader election parameters is a double-edged sword. Increasing the least duration stops flapping during network drops, but it also increases the failover recovery time if a master node actually dies. Always keep --renew deadline slightly smaller than --lease duration to give the current leader multiple attempts to renew its lease before the rest of the cluster attempts a takeover.
Production Incident 17. During a critical minor version cluster upgrade, the control plane update process suddenly fails, leaving the cluster in a partially upgraded, unstable state with some components running deprecated APIs. The upgrade engine reports version skew mismatches, and several custom operators are crash looping due to missing schema definitions. What is your containment and remediation strategy?
Answer: this is a schema incompatibility upgrade failure. I would isolate and recover the control plane version using these steps. 1. Assess version skews. Run explicit check expiration and version queries on the nodes to map the actual version skew of all active kubectls. 2. Scan for deprecations. Execute local linting scanners directly against the cluster namespaces to locate active deprecated schema endpoints. 3. Roll back minor versions. Reapply the target stable version manifest of the control plane to force the API server containers to roll back. 4. Resolve custom schemas. Upgrade the custom resources definition CRDs of the crash looping operators to support the modern schemas required by the target version. Pro tip: never attempt minor version Kubernetes upgrades without a static API audit. Always use tools like Pluto or Kube, no trouble kubectl in your CI and CD pipelines, to scan active Helm charts and manifest files for deprecated API groups that are slated for removal in the target version. Here is Bash configuration, demonstrating how to scan the cluster for deprecated API versions before performing a control plane upgrade. Disclaimer: always test code in a non-production environment. This code scans Helm deployments across all namespaces to identify deprecated API endpoints in active use, preventing schema compilation failures during subsequent Kubernetes upgrades.
Production Incident 18. After performing a database-heavy schema upgrade on a critical custom resource definition CRD, all write operations to that resource suddenly fail with conversion webhook timeout errors. The control plane cannot convert custom objects from the old storage version to the new version, causing critical internal platform services to fail. How do you resolve this webhook conversion failure?
Answer: this is an API schema conversion failure. I would immediately inspect the custom resource definition kubectl, get CRD name -o YAML to locate the registered conversion webhook endpoint, and evaluate the webhook services logs. Since custom resource writes are blocked, I would temporarily roll back the CRD configuration to use direct non-webhook schema mapping if the schemas are structurally identical, or use an emergency patch to decrease the webhook timeout values, preventing the API server from hanging on conversion operations. To resolve the root cause, I would verify the TLS certificates of the conversion webhook server, as expired cert manager webhooks are the most common cause of these silent timeouts, and rerun the conversion webhook pod deployment to establish clean handshakes. Pro tip: always maintain support for at least 2 previous API schema versions in your conversion webhook code. When upgrading a CRD, verify that the spec.versions list in the CRD manifest designates only one version as the storage. True engine, and always pre-validate your webhook against old schema payloads in a staging environment to prevent database-level upgrade lockouts.
Production Incident 19. An automated application team deploys a buggy operator that registers 50,000 unique custom resource CR instances, each containing massive, unpruned JSON payloads with redundant nested metadata fields. The etcd database size triples in hours, and API server serializations slow down to a crawl, dragging down cluster performance. How do you re-architect the CRD configuration to optimize serialization?
Answer: this is an etcd storage bloating crisis. I would resecure the custom resource schemas using these steps. 1. Analyze CR sizes. Execute dynamic loop queries directly on etcd to identify the raw size footprint of the registered custom resource instances. 2. Enforce strict schema pruning. Modify the CRD schema definition to disable unknown field preservation. 3. Prune metadata fields. Remove any heavy, non-essential status parameters from the resource specification schema. 4. Implement client-side validation. Enforce open API schema validation to reject any incoming custom payloads exceeding 100 kilobytes in size. Pro tip: by default, CRDs preserve undeclared fields, allowing clients to write garbage data to etcd. Always configure Kubernetes preserve unknown fields, false at the root of your open API v3 schemas, to force the API server to strictly drop undeclared parameters during serialization. Here is Kubernetes configuration demonstrating how to prune dynamic fields in a custom resource definition to optimize etcd storage footprints. Disclaimer: always test code in a non-production environment. This code disables preservation of undeclared dynamic fields, directing the API server to strictly prune any undocumented JSON parameters from the payload before writing to etcd.
Production Incident 20. During a massive scaling event, where a cluster autoscaler adds 500 new worker nodes simultaneously, the primary control plane nodes experience extreme CPU and network saturation. The Kube API server becomes unresponsive, causing existing nodes to lose heartbeat connection, flip to not-ready state, and trigger a catastrophic, cascading eviction of thousands of healthy production pods. How do you stabilize the control plane during massive scaling events?
Answer: this is a control plane collapse caused by scaling burst saturation. I would immediately isolate the control plane nodes from further ingress traffic by temporarily modifying the cluster load balancer rules to drop external incoming traffic, allowing the API server to focus exclusively on internal node heartbeats. Next, I would modify the kubelet configurations on the newly added nodes to increase the -- node status update frequency, and adjust the API server configuration flags -- node monitor grace period to 120 seconds to prevent false evictions during transient latency peaks. Once node heartbeats stabilize, I would re-enable load balancer ingress traffic and implement strict cluster autoscaler rate limiting configurations, restricting the maximum number of parallel node additions to 50 nodes per batch. Pro tip: in massive cluster environments, default node controller settings are highly aggressive. Always increase the -- node monitor grace period to at least 2 minutes, and utilize the modern node lease feature configured automatically in modern Kubernetes to isolate node heartbeats into dedicated, lightweight lease resources, shielding the core API server from the heavy serialization load of full node status updates.
Category 1 Conclusion: Mastering the Kubernetes control plane.
The Kubernetes control plane is the ultimate administrative authority. As we have seen in these first 20 production incidents, when your API server saturates, or your etcd database experiences space quota exhaustion, your entire system loses its coordination capability. Securing the control plane is not about preventing load, but about designing absolute resilience by hardening admission webhooks, configuring strict API priority and fairness limits, and maintaining pristine etcd keyspace health. With the master nodes fully secured, we must now turn our attention to the physical execution layers.
The universal interview tip: whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Transition from Category 1 to Category 2.
But even the most stable control plane cannot run a container without physical hardware. If the control plane is the nervous system, then your worker nodes are the muscles. When worker nodes experience kernel panics, container runtime leaks, or contract table overflows, the master node's requests can no longer be executed. We must now leave the administrative loop and move directly into the operating system and bare metal configurations. Worker node and OS level incidents. Let's explore Category 2.
Category 2. Worker node and OS level incidents.
Worker nodes are where your platform meets physical reality. In this category, we dive into the high-stakes failures that occur at the operating system and hardware layers, from kubelet memory exhaustion and silent log bloating to contract table saturation and IPVS routing corruption. We will test your ability to debug deep systems failures, isolate noisy neighbors, and keep the compute foundation stable under heavy production load.
Category 2. Worker node and OS level incidents 21 to 40.
Here are the 20 production incidents covering worker node and OS level failures. Production incident 21. Worker node entering not ready state kubelet unresponsive. Production incident 22. Node resource exhaustion CPU, memory, disk, inode, ephemeral storage. Production incident 23. Killer specifically targeting and killing the kubelet process. Production incident 24. Node PID limit exhaustion or zombie processes exhausting PID namespace. Production incident 25. Unrotated container logs silently filling node disks. Production incident 26. AI or GPU incidents. NVIDIA device plugin failures, CUDA driver mismatches, or GPU resource fragmentation MIG. Production incident 27. Noisy neighbor workloads starving other applications. Production incident 28. Kernel panic crashing production worker nodes. Production incident 29. Contract table overflow dropping network traffic. Production incident 30. IP tables, NF tables, or IPVS corruption breaking cluster networking. Production incident 31. Overlay file system corruption after node reboot. Production incident 32. Container runtime crash container D or CRIO or shim leaks consuming node resources. Production incident 33. C group v2 migration breaking older workloads. Production incident 34. Kubelet certificate rotation failure. Production incident 35. Immutable OS or node image rollout failure bottle rocket or Talos. Production incident 36. SSH inaccessible during production incident investigation. Production incident 37. Node drain blocked by misconfigured PDBs. Production incident 38. Stuck terminating pods preventing node maintenance. Production incident 39. Node clock drift causing certificate or authentication issues. Production incident 40. Spot or preemptible node mass interruptions causing workload instability. Total 20 production incidents for worker node and OS level. Let's start with production incident 21.
Production incident 21. A high-density worker node suddenly enters a not-ready state, causing the master node to initiate cascading pod evictions that saturate the virtual network. Upon SSHing into the host, you find that the system memory is heavily utilized and the kubelet is completely unresponsive. What is your troubleshooting and recovery approach?
Answer: this is a host-level system starvation incident. I would troubleshoot and recover the node status using these steps. 1. Audit kubelet health. Run a diagnostic status query directly on the systemd init subsystem to verify if the kubelet daemon process has frozen or crashed. 2. Analyze systemd logs. Inspect the last 100 lines of systemd journals for the kubelet service to identify specific connection or memory errors. 3. Identify memory starvers. Execute host-level memory queries to pinpoint exactly which containerized processes are consuming the node's memory allocation. 4. Restart the daemon. Restart the kubelet daemon process via systemd to temporarily force the node back to a ready state while system processes are optimized. Pro tip: kubelets typically crash because they run out of host memory. Never let user workloads consume 100% of a node's physical RAM. Always configure reserve configurations like system reserved and kube reserved to safeguard the operating system and the kubelet daemon from memory-hungry container runtimes. Here is bash configuration, demonstrating how to troubleshoot and recover an unresponsive kubelet to restore node readiness. Disclaimer: always test code in a non-production environment. Here is the code displaying the runtime status of the kubelet service, allowing us to inspect active daemon failures or startup hangs. This code retrieves the last 100 lines of systemd logs for the kubelet service to isolate the exact error triggering the not ready status.
Production Incident 22. A high concurrency worker node triggers a disk pressure alarm, blocking all scheduling and terminating non-essential workloads. Upon logging into the node, you find that although physical disk space shows 40% free, the node file system has reached 100% inode exhaustion due to millions of tiny orphan temporary files. What is your containment and remediation strategy?
Answer: this is an OS-level file allocation exhaustion. I would resolve the inode blockage using these commands. 1. Locate sticky handlers. Run an open file audit to identify active processes that are keeping deleted but unlinked files open in memory, preventing inode reclamation. 2. Clean stopped containers. Execute a manual garbage collection via the Container Runtime Interface SRE tool to purge stopped container logs and dangling volumes. 3. Identify bloated directories. Run a file system directory analysis to find the specific paths containing the highest count of tiny files, often in the container runtime cache directories. 4. Force inode purging. Clean up orphan temp directories and adjust the kubelet's eviction thresholds to trigger disk cleaning before hard inode limits are hit. Pro tip: standard disk monitoring tools only watch gigabytes, missing inode counts entirely. In high concurrency clusters such as those running rapid CI and CD jobs, always configure your APM to watch node_filesystem_ in nodes_free and optimize container logs to prevent millions of microfiles from silently locking up the node. Here is bash configuration, demonstrating how to find deleted open files and reclaim inode capacity to resolve node disk pressure. Disclaimer: always test code in a non-production environment. Here is the code auditing active processes that are holding open handles to deleted files, preventing the operating system from freeing physical inode blocks. This code triggers the purging of all stopped containers, freeing orphaned volume mounts, and reclaiming raw directory nodes.
Production Incident 23. During a sudden memory surge caused by a memory-leaking application, the Linux kernel's out-of-memory killer is triggered. Instead of killing the rogue application container, the killer unexpectedly terminates the kubelet process itself, disconnecting the entire node from the control plane and causing major operational chaos. How do you re-architect the host limits to prevent this?
Answer: this is a system resource reservation failure. I would reconfigure the kubelet limits using these steps. 1. Evaluate reserve allocation. Check the current /var/lib/kubelet/config.yaml to verify if resource reservations are defined for system daemons. 2. Enforce system resource reserves. Configure explicit system reserved and kube reserved memory limits in the kubelet configuration to insulate critical host processes. 3. Define eviction thresholds. Implement hard eviction limits to force the kubelet to gracefully evict burstable pods before the operating system's kernel killer takes action. 4. Adjust kubelet score. Verify that the system startup configuration for the kubelet sets its score adjust parameter to -999, making it virtually immune to kernel-level terminations. Pro tip: by default, the Linux kernel treats the kubelet like any other user process during memory pressure. Always configure explicit resource reservations in kubelet configuration and verify that the kubelet systemd unit configures its score adjust to ensure that standard pods are evicted long before the system's management daemon is threatened. Here is Kubernetes configuration demonstrating how to set kube reserved and system reserved memory allocations to prevent kubelet kills. Disclaimer: always test code in a non-production environment. This code configures the reserved memory limit for standard operating system background services, protecting the host system from being starved by user container workloads. Here is the code defining the hard eviction thresholds, allowing the kubelet to gracefully evict burstable pods before the host operating system's kernel killer terminates critical system runtimes.
Production Incident 24. A developer deploys a flawed application containing a recursive multi-threading bug. Within minutes, the application launches a fork bomb attack, spawning 32,000 threads and completely exhausting the host operating system's process ID PID namespace. The entire node freezes, and no administrative commands can be run. How do you contain and prevent this?
Answer: this is a host-level namespace exhaustion failure. I would configure a strict process ceiling using these steps. 1. Inspect kubelet PID limits. Audit the active kubelet configuration schema to see if the pod PIDs limit parameter is defined. 2. Enforce pod level limits. Configure an explicit pod PIDs limit inside the kubelet configuration to restrict any single pod's process execution tree. 3. Verify host level system limits. Access the host system configurations and update /etc/sysctl.d/ to increase the maximum system-wide kernel PIDs limit. 4. Apply container limits. Deploy a validating policy like Kyverno to reject any new application pods that attempt to run without a restricted PID profile. Pro tip: default Kubernetes configurations do not restrict the number of process IDs a single pod can spawn. Always configure pod PIDs limit in your global kubelet configuration to a reasonable threshold, for example, 4096, to isolate fork bomb bugs and prevent a single container from starving the host node's PID namespace. Here is Kubernetes configuration demonstrating how to enforce pod PIDs limit to prevent zombie processes from exhausting the host PID namespace. Disclaimer: always test code in a non-production environment. This code configures the maximum number of concurrent process IDs a single pod is allowed to spawn, isolating fork bomb attacks and preventing zombie processes from exhausting the host PID namespace.
Production Incident 25. A high-velocity payment processing container suffers a debugging configuration error, outputting gigabytes of verbose logs to standard out. The unrotated container logs silently fill up the primary node's OS disk partition, triggering a sudden disk pressure alarm that halts transaction processing during peak hours. How do you resolve and prevent this?
Answer: this is a runtime logging rotation failure. I would implement these steps to secure the host file system. 1. Identify bloated logs. Locate the specific logging file path inside /var/log/pods to identify which container is generating the volume spike. 2. Manually rotate logs. Execute a manual truncation of the bloated log file on the host operating system to immediately relieve disk pressure. 3. Configure kubelet limits. Implement strict container log max size and container log max file settings within the primary kubelet configuration file. 4. Automate logrotate rules. Verify that the system's background logrotate service is active and configured to sweep Docker or containerd logs regularly. Pro tip: standard Linux logrotate configurations are often too slow for container speeds. Always configure the kubelet itself to manage log rotations by setting container log max size to a compact threshold, for example, 10 MB, and limiting the maximum files retained to ensure log storage is bounded automatically. Here is Kubernetes configuration demonstrating how to configure container log max size and container log max files to prevent unrotated container logs from filling node disks. Disclaimer: always test code in a non-production environment. This code configures the maximum size threshold for a single container standard out log file before the kubelet forces a log rotation. Here is the code specifying the maximum number of rotated log backup files the node will retain, ensuring old logging blocks are continuously purged to protect disk space.
Production Incident 26. A newly deployed AI model training workload fails to schedule, throwing insufficient nvidia.com/GPU errors across all node pools. Upon checking the GPU node group, you discover that while physical GPUs are completely idle, a minor CUDA driver mismatch between the host OS kernel and the NVIDIA Container Toolkit daemon is preventing the NVIDIA device plugin from initializing, taking the entire GPU allocation offline. How do you troubleshoot and fix this driver mismatch?
Answer: this is a hardware to runtime abstraction failure. I would first SSH into a GPU worker node and execute the NVIDIA SMI utility tool to verify if the host kernel can still communicate with the underlying hardware, which isolates whether the issue is a dead GPU or a runtime integration mismatch. Next, I would analyze the logs of the NVIDIA device plugin daemon set pods in the kubesystem namespace to locate specific API version or driver incompatibilities. To resolve the mismatch cleanly without constantly patching OS images, I would align our node provisioning templates such as an EKSAMI or customized cloud init to use a unified NVIDIA driver version, and update our container runtime configuration /etc/containerd/config.toml to explicitly register the NVIDIA runtime classes. This ensures the container runtime correctly utilizes the host GPU libraries, restoring allocation reporting to the master scheduler. Pro tip: AI workloads are highly sensitive to driver skews. Never manage GPU node drivers manually. Always utilize immutable node operating systems like BottleRocket that bundle validated kernel, CUDA, and container toolkit configurations together. And configure strict validation checks in your CI and CD pipelines to ensure matching base image layers are deployed for all AI workloads.
Production Incident 27. A legacy, unthrottled monolithic pod is deployed without resource requests and limits. During peak processing hours, it launches a CPU-intensive batch process, consuming 100% of the host CPU and starving several high-priority microservices on the same node, causing massive API timeouts. How do you isolate these noisy neighbors and protect business-critical workloads?
Answer: this is a quality of service QoS classification failure on the node. I would immediately configure a strict limit range policy on the affected namespaces to automatically inject default resource requests and limits for any pod deployed without them, which instantly moves unthrottled workloads from the unstable best effort class to the controlled burstable QoS class. Next, I would refactor our production application deployment manifest to define matching CPU requests and limits, upgrading their scheduling status to the guaranteed QoS class. This forces the operating system's kernel-level, completely fair scheduler CFS to prioritize their cycles and throttle the CPU allocation of the noisy neighbor container when the node hits 100% utilization, maintaining stable API response times. Pro tip: in Kubernetes, QoS classes dictate node survival. A best effort pod is always the first to be killed and throttled during resource shortages. Always enforce strict limit ranges and resource quotas at the namespace level to ensure every container has a baseline resource request, effectively neutralizing noisy neighbors and shielding guaranteed production traffic.
The universal interview tip: whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 28. A hardware-level memory failure triggers a kernel panic on a critical bare metal worker node, causing the host to freeze instantly. However, the node fails to reboot, remaining in a silent, hung state where it cannot respond to the control plane, delaying the cluster autoscaler from detecting the hardware failure and launching replacements. How do you configure the kernel to force an automatic reboot?
Answer: this is a kernel error handling failure. I would configure sysctl parameters to enforce automatic host reboots using these steps. 1. Access system configurations. SSH into a staging worker node and navigate to the sysctl configuration directory /etc/sysctl.d/ to create a dedicated panic tuning file. 2. Configure panic reboot timeout. Append the kernel.panic parameter to the configuration file, specifying a 10-second automatic reboot delay. 3. Force panic on oops. Add the kernel.panic_on_oops flag to force the node to reboot immediately if an out-of-memory kernel error occurs, preventing silent lockups. 4. Apply parameters globally. Reload the system parameters on the host to immediately apply the kernel protections without requiring a node reboot. Pro tip: default Linux kernel settings do not automatically reboot after a panic, leaving frozen nodes in a ghost state that blocks automated recovery. Always configure your OS images with kernel.panic = 10 and kernel.panic_on_oops = 1 to force physical reboots, allowing the cluster autoscaler to quickly identify the lost node and reschedule the affected workloads. Here is bash configuration, demonstrating how to configure sysctl parameters to force an automatic node reboot during kernel panics. Disclaimer: always test code in a non-production environment. This code configures the kernel reboot timeout, forcing the physical node to automatically reboot 10 seconds after a kernel panic occurs, so the cluster autoscaler can detect the failure. Here is the code configuring panic on oops, which ensures the node immediately halts and reboots if a driver or module crashes, preventing the node from lingering in a corrupt, silent state.
Production Incident 29. During a high concurrency event, your API gateway pods begin dropping inbound network connections intermittently. Host-level diagnostics reveal that the Linux kernel's network connection tracking contract table has overflowed, resulting in a deluge of dropped packets and connection timeouts. How do you scale the contract capacity?
Answer: this is a kernel-level network connection tracking limit failure. I would scale the contract limits using these commands. 1. Audit current contract limits. Check the current maximum tracking capacity by querying the kernel parameters directly via sysctl. 2. Increase contract table size. Increase the nf_contract_max parameter to allow the kernel to track up to 1 million concurrent connections. 3. Optimize timeout parameters. Reduce the established connection timeout from 5 days to 10 minutes to quickly flush idle connection states from memory. 4. Verify local host tuning. Save the network tracking parameters permanently inside the node configuration templates to survive OS reboots. Pro tip: High-traffic microservice environments quickly overwhelm default Linux connection tracking tables. Always scale net.netfilter.nf_contract_max to at least 10.48576 on high-throughput worker nodes. And aggressively lower established TCP timeouts to prevent stale connections from exhausting system tracking buffers. Here is bash configuration, demonstrating how to scale netfilter contract table limits to prevent packet drops during high concurrency traffic spikes. Disclaimer: always test code in a non-production environment. This code configures the maximum size of the contract table, expanding the connection tracking capabilities of the kernel to prevent connection timeouts under load. Here is the code reducing the established connection timeout, forcing the kernel to quickly purge idle connection states from memory and protect tracking capacity.
Production Incident 30. Following a massive scaling burst, pod-to-pod networking breaks completely across several worker nodes. You discover that IP tables rules inside the host OS have become corrupted because the kube proxy daemon failed to acquire the system lock while writing new routing rules, causing a complete synchronization deadlock. How do you debug and resolve this routing corruption?
Answer: this is a network routing synchronization deadlock. I would first SSH into an affected worker node and check the logs of the local kube proxy pod in the kube system namespace to locate specific IP tables lock timeout or synchronization retry failures. Next, I would execute a host-level dump of the active routing tables to verify if the virtual cluster IP endpoints match the actual backing pod IPs. To resolve the synchronization lock immediately, I would execute a system command to manually flush the IP tables rules IP tables-f and restart the local kube proxy container pod, which forces kube proxy to rebuild the entire rule chain from scratch. To prevent a recurrence on high-scale clusters, I would reconfigure the kube proxy configuration map to transition its routing mode from the resource-heavy IP tables mode to the high-performance IPVS IP virtual server mode, which handles millions of routing updates using efficient hash tables instead of linear rule evaluations. Pro tip: standard IP tables mode executes sequentially and struggles at scale, as updating a single rule requires writing the entire rule set back to the kernel. For any cluster running more than 5,000 active service endpoints, always migrate kube proxy to IPVS mode to eliminate IP tables lock contention and reduce CPU overhead from packet routing. Here is Kubernetes configuration demonstrating how to migrate kube proxy from IP tables to IPVS mode to eliminate rule synchronization deadlocks. Disclaimer: always test code in a non-production environment. This code switches the routing engine to IPVS, which uses hash tables instead of IP tables rules to prevent the proxy from locking up during updates. Here is the code setting the load balancing scheduler to round robin, which distributes incoming connections evenly across all healthy pods.
Production Incident 31. Following a sudden host reboot after a hardware maintenance event, a critical worker node fails to start its containers. The containerd logs show mount failures because the underlying overlay 2 storage directories got corrupted on the XFS partition. With dozens of pods blocked from booting, what is your containment and remediation strategy?
Answer: this is a storage mount failure caused by file system corruption. To prevent further disk damage, I would stabilize the node and repair the file system using these steps. 1. Stop the container runtime. Stop the containerd service immediately via systemd to guarantee that no active write operations can corrupt the disk metadata further. 2. Repair the file system. Run a non-destructive check on the underlying XFS block device to find and repair any metadata inconsistencies. 3. Isolate the state directories. Instead of running a risky deletion, rename the corrupt task state directory under /var/lib/containerd to isolate it for debugging. 4. Restart and verify. Restart containerd and check the system logs to ensure that local container mounts are completing without error. Pro tip: XFS metadata corruptions are common after ungraceful reboots. Always run your host file systems with the ftype = 1 option enabled to ensure overlay 2 has proper directory type support, and automate a disk check script on startup to catch file system errors before containerd attempts to boot. Here is bash configuration, demonstrating how to check for XFS file system errors and clean up corrupt container storage directories. Disclaimer: always test code in a non-production environment. This code stops the container runtime daemon, ensuring no active writes are occurring while we inspect the underlying file system. This code checks the root storage partition for file system errors without writing any changes to disk.
Production Incident 32. Monitoring alerts show that a worker node's memory usage is creeping up, even though pod traffic is flat. You find that containerd shim processes are leaking and lingering in memory after pods are deleted, eventually exhausting the node's process limits and crashing the runtime. What is your troubleshooting and containment strategy?
Answer: this is a container runtime leak. I would audit the leaked processes and reclaim system limits using these commands. 1. Audit process hierarchy. Query the host process tree to list all containerd shims and filter for those with a parent process ID of 1, which indicates they have been orphaned. 2. Trace open sockets. Check active Unix sockets to verify if the orphaned shims are still holding open stale file descriptors. 3. Gracefully kill the orphans. Send a termination signal to the orphan shim process IDs to release the leaked host memory. 4. Perform a safe restart. Restart containerd to force a cleanup of any zombie processes without disrupting active, healthy container tasks. Pro tip: leaked shims often occur because of broken log pipes or hung I/O inside custom sidecars. Always upgrade your container runtime to a stable patch version that includes automatic orphan reaping, and configure system monitoring to alert if the ratio of containerd shim processes to active pods exceeds 1.2 to 1. Here is bash configuration, demonstrating how to find orphaned container shims and safely restart the runtime without dropping active pods. Disclaimer: always test code in a non-production environment. This code lists all active containerd shim processes on the node, filtering for a parent process ID of 1, which identifies orphaned shims left behind by containerd. Here is the code sending a graceful termination signal to the leaked process ID to clean up the stale system handles.
Production Incident 33. Your platform team upgrades the node operating system across your staging cluster, which migrates the host container runtime to C Group v2. Immediately, several older Java applications begin crash looping without memory errors, even though their memory limits haven't changed. How do you troubleshoot and fix this migration failure?
Answer: this is a C Group compatibility issue. Older Java runtimes like early Java 8 or 11 builds do not understand the new C Group v2 directory layout. Because they cannot read the memory limit files correctly, they assume they have access to the entire host's physical RAM, leading to JVM heap miscalculations and instant kills inside the container. To fix this immediately for running workloads, I would manually hardcode the heap limits by adding the -xmx or -xx max RAM percentage flags to the application deployment specs. To fix this permanently across the platform, I would update our base container images to a newer JDK patch version that natively supports C Group v2, or configure our node bootstrap scripts to fall back to C Group v1 using kernel boot arguments. Pro tip: never upgrade your host OS to a modern version with C Group v2 enabled by default without auditing your legacy application runtimes. Older JVMs, Go runtimes, and systemd-based containers will misread the system metrics, resulting in CPU throttling and kills because they cannot see the container limits correctly.
Production Incident 34. A worker node's client certificate expires, and the node instantly drops out of the cluster. You find that the kubelet failed to auto-rotate its TLS certificate because the API server certificate signing request CSR auto-approval loop was misconfigured, blocking the node from renewing its credentials. What is your remediation plan?
Answer: this is an auto-rotation failure caused by missing access controls. I would resolve the RBAC blockage and approve the certificates using these steps. 1. Check kubelet settings. Verify that rotate certificates is set to true in the node's local/var/lib/kubelet/config.yaml file. 2. Locate blocked requests. Query the API server for pending certificate signing request CSRs matching the broken node. 3. Fix the auto-approval RBAC. Deploy a cluster role binding that grants the node's group permission to auto-approve their own client renewals. 4. Manually approve the pending CSR. Run an administrative approval command on the blocked CSR to instantly bring the node back online. Pro tip: enabling rotate certificates. True in the kubelet is only half the battle. If your cluster administration roles do not grant the system certificates.k8.io certificate requests self-node client permission to node groups, the API server will reject the renewal requests, leaving your nodes to disconnect silently every year. Here is Kubernetes configuration, demonstrating how to enable automatic client certificate rotation in the kubelet configuration. Disclaimer: always test code in a non-production environment. This code binds the built-in system role responsible for auto-approving node client certificate renewal requests directly to the nodes group.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 35. You decide to migrate your cluster to BottleRocket, an immutable container-optimized operating system. However, during the rollout, a critical security logging daemon set fails to deploy because it attempts to mount and write to /user and /bin, which are read only on BottleRocket. How do you resolve this immutable OS rollout failure?
Answer: this is a security architecture conflict. The security agent crashed because it tried to write to /user or /bin, which are completely locked down and read only on BottleRocket to block host-level tampering. To resolve this, I would change the logging agent's daemon set configuration, shifting its host path mounts from the restricted system directories to the writable /var partition, which is dedicated for container runtimes and persistent logs. If the agent absolutely must execute binary commands on the host, I would configure a BottleRocket control container to run a secure sidecar that interacts with the host via APIs rather than direct file system writes. Pro tip: running security or monitoring agents on immutable OS hosts requires a shift in how you mount directories. Never attempt to force write access to /user or /bin. Always use /var or /temp for writable daemon set storage, and use the official, vendor-provided APIs like BottleRocket API or Talos gRPC to configure host-level parameters.
Production Incident 36. A high-priority production node gets stuck in a CPU starvation loop, causing workloads to time out. When you try to log into the host via SSH to run diagnostics, the connection times out because the node's SSH daemon is starved of resources. How do you bypass SSH to troubleshoot the node?
Answer: SSH is dead because the node is starved. I would bypass the SSH daemon and access the host using these steps. 1. Deploy a privileged debug pod. Use kubectl to launch a debugging pod that targets the affected node name directly. 2. Access host namespaces. Configure the debug command to run with host networking, PID, and IPC namespace access. 3. Mount the root file system. Access the host's physical disk partition mounted inside the debug container at /host. 4. Isolate the resource consumer. Run containerized shell utilities within the host namespace to locate and terminate the high CPU processes. Pro tip: when SSH locks up, kubectl debug node is your ultimate backdoor. It launches a privileged pod directly on the host node, mounting the host's root directory to /host, and giving you full root command access to the operating system, even when the standard SSH daemon is dead. Here is bash configuration, demonstrating how to use a privileged debug container to bypass SSH and access a hung node. Disclaimer: always test code in a non-production environment. This code launches a privileged pod directly in the host's namespaces, giving you a root shell on the node even when the SSH daemon is completely unresponsive.
Production Incident 37. A platform engineer triggers an automated node upgrade, but the node drain hangs indefinitely. You discover that a misconfigured pod disruption budget (PDB) has set max unavailable, 0 for a single replica payment gateway deployment, completely blocking the maintenance window. What is your containment and remediation strategy?
Answer: this is a maintenance block caused by strict policy configurations. Since forced draining does not bypass PDBs, I would resolve the block using these steps. 1. Locate the blocking policy. Query the pod disruption budgets in the namespace to identify the specific rule preventing eviction. 2. Temporarily remove the PDB. Delete the blocking pod disruption budget object via the API server to clear the eviction constraint. 3. Execute the node drain. Run a standard node drain command to safely evict the remaining healthy pods. 4. Restore and correct the budget. Reapply the pod disruption budget with a corrected configuration such as max unavailable, one to ensure future upgrades can proceed safely. Pro tip: pod disruption budgets can easily paralyze cluster operations. Never let a single replica deployment run with max unavailable, 0 or min available, 100%. Always configure your CI and CD linter to block these configurations, and use the --force -grace period equals 0 flags during emergency maintenance to bypass PDB blocks. Here is bash configuration, demonstrating how to temporarily delete a blocking pod disruption budget to allow a node drain to proceed. Disclaimer: always test code in a non-production environment. This code deletes the blocking pod disruption budget temporarily, allowing the eviction API to proceed with draining the node's pods. This code executes the standard node drain, safely evacuating the remaining workloads now that the policy constraint is cleared.
Production Incident 38. During a routine node drain, several pods get stuck in a terminating state forever. The drain is blocked because a dead NFS mount inside the containers is hanging, preventing the kubelet from unmounting the volumes and cleaning up the namespaces. What is your troubleshooting and recovery approach?
Answer: this is a storage-level mount deadlock. I would force delete the pods from the API server and clean up the stale mounts using these steps. 1. Force delete the pod. Execute an emergency deletion with 0 grace period to force the API server to clear the pod metadata from etcd. 2. Strip stuck finalizers. Run a metadata patch to clear the finalizers array, unblocking the logical deletion pipeline. 3. Execute a lazy host unmount. SSH into the node and run a lazy, forced unmount on the dead NFS mount path. 4. Verify kubelet cleanup. Check the node directories under /var/lib/kubelet/pods to ensure the local volume structures are fully cleaned up. Pro tip: stripping finalizers and force deleting pods is a high-risk fallback. It tells the API server to forget the pod, but it can easily leave orphaned volumes mounted on the host node. Always perform a lazy unmount umount-f-l on the host afterward to prevent disk leaks and directory lockups. Here is bash configuration, demonstrating how to force delete a stuck pod and strip its finalizers using a JSON patch. Disclaimer: Always test code in a non-production environment. This code tells the control plane to immediately stop waiting for the kubelet's cleanup confirmation and delete the pod representation from etcd. Here is the code patching the pod's metadata to clear out any dead finalizers, allowing the resource to be completely removed.
Production Incident 39. An application team reports that their pods can no longer access external cloud resources or authenticate with HashiCorp Vault. You discover that the host node's system clock has drifted by 5 minutes due to a stopped NTP daemon, causing all outgoing TLS handshakes and security token validations to fail. How do you recover and prevent this clock drift?
Answer: this is a security handshake failure caused by node clock drift, because security protocols like TLS, OIDC, and Vault authentication rely on precise timestamps to validate token expiration windows. A clock skew of more than a few seconds will cause all outgoing handshakes to be rejected immediately. To recover the node, I would SSH into the host and run systemd commands to restart the cronid or NTPD service, forcing an immediate time synchronization with the configured upstream NTP pool. To prevent a recurrence, I would configure a node problem detector daemon set to monitor local time health and implement Prometheus alerts targeting node_timex_offset_second to flag any node experiencing a clock drift of more than 500 milliseconds before it disrupts workload authentication. Pro tip: cloud infrastructure runs on time. A minor clock drift of 1 minute will silently break AWS IAM authentication, Vault token validation, and JWT validation. Always configure Crony with high-frequency sync intervals on your host operating system images, and monitor the NTP offset across your entire fleet.
Production Incident 40. AWS triggers a massive Spot instance reclamation event, terminating 80% of your Spot-backed worker nodes in a single availability zone within a 2-minute window. The sudden rush of orphan pods overflows the scheduler queue, causing widespread application downtime. How do you re-architect the cluster to handle Spot interruptions?
Answer: this is an auto-scaling capacity failure under high-rate disruption. To protect the application cluster from sudden Spot terminations, I would evaluate migrating our node management to Carpenter, which handles Spot instance lifecycles and schedules resources faster. I would configure our node pools to enforce a diversified compute strategy, blending different instance types such as M5, C5, and R5 classes across multiple availability zones, so a single Spot pool exhaustion does not wipe out our entire compute capacity. Lastly, I would deploy a local node termination handler to listen directly to the cloud provider's metadata endpoint, giving our workloads a 2-minute warning to gracefully drain connections and reschedule on on-demand fallback nodes before the Spot instances are physically reclaimed. Pro tip: running 100% of your production database or stateful workloads on Spot nodes is an anti-pattern. Always maintain an on-demand node pool dedicated for core platform services and critical stateful systems, and use Carpenter's disruption policies with strict node affinities to ensure your stateless workloads are distributed across diversified Spot capacities.
Category 2 Conclusion. Mastering node and operating system failures.
Worker nodes are the front line of your cluster's computing power. As we have seen in these 20 incidents, host stability is not just about allocating CPU and RAM. It is about managing deep OS-level boundaries like contract limits, kernel panic behaviors, PID namespaces, and disk I nodes. A true platform engineer does not solve a host failure by casually wiping directories or aggressively force draining nodes. Instead, they stabilize the runtime, isolate corrupted paths, and implement defensive configurations like explicit cube reserved memories and IPv4 hash routing. By hardening the operating system layer, you build a stable foundation that keeps your workloads running under extreme enterprise pressures.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Transition from Category 2 to Category 3.
But even on a perfectly tuned host, your application workloads have their own complex life cycles to navigate. If the worker nodes are the compute foundation, then the pods are the actual working engines. When those engines start up, they must pull container images, mount external secrets, pass health checks, and balance across availability zones. When any of these steps fail, whether due to image pull off limits, stale config map mounts, or scheduling constraints, the application stalls. We must now move from the raw host operating system to the orchestration of the workload itself. Pod and workload lifecycle incidents. Let's explore Category 3.
Category 3. Pod and Workload Lifecycle Incidents.
Pod scheduling, startup, and execution represent the active lifecycle of your platform's applications. In this category, we dive into the high-severity failures that occur during deployment, scaling, and termination phases, from crash loop back-off loops and broken readiness checks to subpath config staleness and stateful storage lockups. We will test your ability to debug container startup failures, align resource requests with actual runtime behaviors, and keep application lifecycles fluid under real-world pressures.
Category 3. Pod and Workload Lifecycle Incidents 41 to 60.
Here are the 20 production incidents covering pod and workload lifecycle failures. Production Incident 41. Crash loop back off after faulty deployment or init container failure. Production Incident 42. Application lifecycle failures, readiness, liveness, startup probe misconfigurations. Production Incident 43. Pod stuck pending because of insufficient resources or node selectors. Production Incident 44. Topology spread constraints, max SKU blocking pod scheduling during a single AZ outage. Production Incident 45. Image pull back off from registry authentication failures or rate limits. Production Incident 46. Killed containers because of memory limit and request issues. Production Incident 47. Secret mount failure breaking workloads. Production Incident 48. Secret or config map mount failures specifically due to subpath staleness. Production Incident 49. Config map corruption causing application instability. Production Incident 50. Stateful set pods failing after node restart. Production Incident 51. Daemon set rollout failure across cluster. Production Incident 52. Sidecar containers consuming excessive resources. Production Incident 53. Namespace resource quota blocking critical deployments. Production Incident 54. Pod security admission or OPA or gatekeeper policies suddenly blocking workloads. Production Incident 55. Kubernetes finalizers blocking resource deletion indefinitely. Production Incident 56. PVC or PV finalizer deadlocks blocking namespace deletion completely. Production Incident 57. Massive namespace deletion stuck for hours. Production Incident 58. Orphaned resources after failed controller reconciliation. Production Incident 59. Preemption and priority class misconfigurations causing collateral workload evictions. Production Incident 60. Pod suddenly evicted due to ephemeral storage exhaustion from unrotated standard out and standard error logs. Total 20 production incidents for pod and workload lifecycle. Let's start with Production Incident 41.
Production Incident 41. A critical payment processing deployment is stuck in a crash loop backoff cycle immediately after a release. The main application logs are completely empty, indicating that the container is crashing before it even initializes, because its prerequisite database migrator init container is failing silently. How do you isolate and debug this startup block?
Answer: the deployment is failing because the database check init container crashed. I would inspect and isolate the startup failure using these diagnostic steps. 1. Inspect container states. Run a wide query on the pod status to confirm which specific init container is failing and check its exit code. 2. Retrieve init logs. Extract the logs of the failed init container directly by specifying the init container name in the log command. 3. Audit manifest specs. Check the environment variables and config mounts assigned to the init container to verify database credentials. 4. Fix database connectivity. Resolve the network connection or credential error in the database security group to unblock the init container's checks. Pro tip: standard logging commands only dump the main application container. When troubleshooting a crash loop backoff, always inspect the init container's state in kubectl, describe pod first, and use the -c flag to read its logs directly, preventing hours of debugging empty main container output. Here is bash code demonstrating how to view the logs of a failed init container to debug a crash loop backoff error. Disclaimer: always test code in a non-production environment. This code specifies the exact init container we want to inspect, allowing us to bypass the main application container logs and see the initialization error directly.
Production Incident 42. A slow-starting Java application is caught in an infinite restart loop during peak traffic scaling. The pod boots up, starts loading its heavy framework into memory, but is repeatedly terminated by the kubelet before it can finish. You find that the liveness probe is configured too aggressively and is killing the app before it is fully active. How do you resolve this lifecycle check failure?
Answer: liveness probes are killing the app before it can finish starting up. I would re-architect the container's probes using these steps. 1. Evaluate boot duration. Measure the actual startup time of the Java container under cold start conditions to determine the required warm-up buffer. 2. Introduce a startup probe. Configure a dedicated startup probe in the deployment manifest to protect the pod during its initial boot phase. 3. Disable active checks during boot. Set the startup probe's failure threshold high enough to allow the application up to 3 minutes to initialize. 4. Set tight liveness checks. Keep the standard liveness probe configured with tight, aggressive intervals once the startup probe confirms the app is fully online. Pro tip: never solve slow startup times by increasing the initial delay seconds on your liveness probe. This leaves your app unprotected during standard execution. Always use a dedicated startup probe to shield the container during boot, keeping your liveness probe aggressive so it can quickly catch deadlocks later. Here is Kubernetes configuration, demonstrating how to use a startup probe to prevent liveness probes from killing slow booting applications. Disclaimer: always test code in a non-production environment. This code configures a startup probe to run first, protecting slow-starting applications by disabling liveness and readiness evaluations until the app is fully initialized.
Production Incident 43. During a sudden marketing campaign launch, your newly scaled customer dashboard pods remain stuck in a pending state indefinitely. Running diagnostics reveals that the pods are requesting more CPU resources than any single worker node in the cluster has unallocated, while some nodes are completely blocked because of restrictive node selectors. How do you resolve the scheduling block?
Answer: the pod is stuck in a pending state because it is asking for more CPU than any single node has left. I would immediately check the scheduling events using kubectl describe pod to confirm the resource exhaustion and locate the unschedulable selectors. To get the workloads online, I would perform a temporary patch on the deployment manifest to lower the CPU requests to a realistic baseline while keeping limits high to allow bursting. Next, I would audit our node labeling structure to ensure the pod's node selector fields align with our active node pool labels. For a permanent fix, I would implement horizontal pod autoscaling based on memory and set up a vertical pod autoscaler VPA in recommendation mode to continuously right-size our container requests based on real-world usage patterns. Pro tip: pods stay pending because of requests, not limits. Schedulers only calculate node capacity using the CPU and memory requests specified in your manifest. Always keep your requests as small as possible to maximize node density, and let your limits handle the peak traffic bursts.
Production Incident 44. A severe thunderstorm causes a complete power loss in a major cloud provider availability zone, a Z1, taking down half of your cluster's worker nodes. Despite having plenty of compute capacity in the remaining healthy zones, a Z2 and a Z3, your application pods refuse to scale up, remaining stuck in a pending state because their strict zone spreading constraints cannot be satisfied. How do you unblock scheduling during the outage?
Answer: a zone went down, and our strict anti-affinity rules are stopping pods from scheduling in the remaining healthy zones. I would bypass this scheduling constraint using these steps. 1. Identify the constraint. Locate the strict topology spread constraints in the active deployment manifest that are enforcing zone-level balance. 2. Soften the scheduling rule. Update the when unsatisfiable parameter in the topology constraints from do not schedule to schedule anyway. 3. Deploy the configuration patch. Apply the updated deployment spec to allow the API server to perform a rolling update of the pending pods. 4. Balance the workloads. The scheduler will now distribute the pending workloads across the remaining healthy availability zones automatically. Pro tip: strict scheduling constraints do not schedule will paralyze your cluster's recovery during a cloud zone outage. Always configure your production topology spread constraints with when unsatisfiable. Schedule anyway to ensure your workloads can automatically consolidate in healthy zones when a disaster strikes. Here is Kubernetes configuration, demonstrating how to use topology spread constraints with a soft scheduling fallback during zone outages. Disclaimer: always test code in a non-production environment. This code sets the zone spreading policy to a soft requirement, letting the scheduler put pods on healthy nodes in remaining zones when an entire zone goes dark.
Production Incident 45. Following a sudden cluster-wide node pool replacement, hundreds of application pods fail to start, getting stuck in an image pull back-off state. Your on-call dashboard shows that the newly created nodes are hitting public Docker Hub rate limits and cannot pull your base utility images, while private database images are failing due to an expired registry credential secret. How do you restore the pull pipelines?
Answer: we are hitting public Docker Hub rate limits on image pulls, and our registry login token expired. I would resolve the authentication and pulling locks using these steps. 1. Verify the pull secret. Audit the target namespace to check if the registry cred secret exists and contains a valid, unexpired login token. 2. Associate credentials globally. Patch the default service account in the namespace to automatically inject the image pull secrets into every new pod. 3. Bypass rate limits. Reroute the public base image paths in our Docker files to pull from our internal, authenticated container registry mirror. 4. Force deployment refresh. Trigger a restart on the pending deployments to force the nodes to pull the images using the new global credentials. Pro tip: forcing developers to manually write image pull secrets in every pod manifest is a massive configuration risk. Always patch your namespace's default service account to include the registry secret globally, and host critical base images in an internal container registry to avoid public Docker Hub rate limits. Here is Kubernetes configuration, demonstrating how to patch the default service account with registry credentials to prevent image pullback off errors. Disclaimer: always test code in a non-production environment. This code binds our registry login secret directly to the service account, ensuring that any pod using this account automatically inherits the credentials to pull images.
Production Incident 46. A high-throughput database caching container is repeatedly terminated with an killed status during traffic surges. Your metrics dashboard shows that although the JVM heap is capped at 2 GB, the container itself is being killed by the kernel when the resident memory size hits its hard C group limit of 2.5 GB. How do you resolve this memory limit misalignment?
Answer: the container is running out of memory because the JVM heap size is misaligned with the container's C group limits. By default, Older Java runtimes are blind to container boundaries, and even modern JVMs require non-heap memory allocations such as metaspace, thread stacks, and garbage collection overhead that are not covered by standard heap flags. To resolve this immediately, I would increase the container's memory limit to 4 GB in the deployment manifest to provide a healthy buffer for non-heap allocations, and configure the JVM to use a percentage-based heap allocation, for example, -XX max RAM percentage equals 75.0. This forces the JVM to dynamically adjust its heap based on the container's cgroup limits, preventing the container from hitting the hard kernel ceiling during high concurrency garbage collection runs. Pro tip: never set your JVM heap size equal to your container's memory limit. A Java container always needs at least 25% to 30% additional memory overhead outside the heap for off-heap tasks, native memory, and thread allocations. Always use percentage-based heap configurations to ensure the JVM scales dynamically with the container limit.
Production Incident 47. A critical microservice deployment stalls during startup, with all pods showing a create container config error status. Running diagnostics reveals that the application is configured to load all its database configurations as environment variables using enwfrom targeting a specific secret, but that secret has been accidentally deleted from the namespace. How do you unblock the deployment?
Answer: the pod is stuck booting because a secret mounted as an environment variable does not exist in the namespace. When you map an entire secret or config map using enwfrom or volume mounts, the container runtime enforces a hard dependency. If the target resource is missing, the kubelet will refuse to start the container to prevent silent runtime failures. To unblock the pipeline immediately, I would create a dummy secret with the expected name containing empty keys, allowing the container runtime to successfully boot the pods. Once the system is stabilized, I would restore the actual configuration keys from our backup repository and refactor the deployment manifest to mark non-essential configuration mounts as optional, true to prevent missing parameters from taking down our entire cluster deployment. Pro tip: using enwfrom creates a strict boot dependency on the secret. If you have non-essential keys, always define them individually in your manifest and set the optional true flag, ensuring your container can still start and gracefully degrade if a minor configuration resource is missing.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 48. Your development team updates a database connection string in a central config map, but they report that their application pods are still attempting to connect to the old database. You find that the config map was mounted inside the containers using a strict sub-path volume mount, which blocks the kubelet from automatically updating the files on disk when the underlying config map changes. How do you resolve this configuration staleness?
Answer: using subpath for mounting configs means the application is running on stale settings because it does not see updates to the config map. I would re-architect the volume mounts using these steps. 1. Identify subpath mounts. Locate the specific subpath declarations in the container's volume mount specifications. 2. Remove subpath constraints. Refactor the deployment spec to mount the entire config map directory instead of targeting individual files via subpath. 3. Expose config files cleanly. Use standard directory volume mounts, which allows the kubelet to automatically symlink and update the files in real time. 4. Trigger workload restart. Perform a rolling restart of the deployment pods to force the application to read the newly updated files from disk. Pro tip: using subpath to mount individual configuration files disables the automatic update mechanism in Kubernetes. When the config map changes, subpath files never refresh on disk without a pod restart. Always mount the entire directory, or use tooling like the reloader operator to automatically trigger rolling updates when configurations change. Here is Kubernetes configuration, demonstrating how to mount a config map as a directory to avoid configuration staleness caused by subpath mounts. Disclaimer: always test code in a non-production environment. This code mounts the entire config map as a directory, allowing the kubelet to dynamically update the configuration files on disk whenever the config map changes.
Production Incident 49. An administrator accidentally writes a typo containing tab characters instead of spaces into a central config map YAML payload, corrupting an application's internal properties file. On startup, the application container crashes immediately because its internal JSON or properties parser fails to parse the malformed data. How do you troubleshoot and recover from this configuration corruption?
Answer: a syntax error in a config map properties file is crashing the app on startup. I would first identify the corruption by running kubectl describe config map to inspect the raw key value payload and locate the invalid characters. Since the application is crashing, I would edit the config map directly to correct the syntax errors, replacing any invalid tab characters with valid YAML-compliant spaces. Once the config map is validated, I would execute a rolling restart on the affected deployment to force the container runtimes to pull the clean, corrected configuration on boot. To prevent future syntax corruptions, I would implement a CI and CD pre-commit hook that validates all config map schemas against a strict linter before they are permitted to write to our GitOps repository. Pro tip: never edit production configurations on the fly without schema validation. Always use dry run validation flags. Kubectl create configmap --dry run equals client -o YAML in your pipelines to ensure that malformed properties or YAML syntax errors are caught before they are committed to etcd.
Production Incident 50. Following a sudden physical worker node crash, your primary stateful database pod gets stuck in a terminating state, while its replacement pod remains stuck pending on a healthy node. The new node is throwing volume already mounted errors because the cloud provider's storage engine still has the physical EBS volume locked and attached to the dead host. How do you safely release the stateful volume?
Answer: a stateful pod is stuck after a node crash because its volume is still locked by the dead node. I would safely release the storage lock and reschedule the database using these steps. 1. Confirm host node death. Verify through the cloud provider console that the physical worker node is completely dead and cannot recover. 2. Force delete the stateful pod. Execute an emergency deletion of the stuck terminating pod with 0 grace period to clear the active lock from the API server. 3. Manually detach the volume. Use the cloud provider's CLI tool to manually detach the physical storage volume from the dead host instance ID. 4. Unblock new scheduling. The Cloud Controller Manager will now detect the detached state, allowing the new node to safely attach the volume and boot the pending database pod. Pro tip: force deleting stateful pods is a high-risk operation. If the dead node is actually alive and experiencing network lag, force deleting the pod can lead to data split brain as two nodes attempt to mount the same volume. Always verify the physical host's power state before force deleting stateful workloads. Here is bash code demonstrating how to force delete a stuck stateful pod and detach its cloud volume during a node crash. Disclaimer: always test code in a non-production environment. This code manually detaches the stuck cloud volume from the dead node, allowing the new node to successfully attach the storage and boot the stateful pod.
Production Incident 51. A platform engineer deploys an update to a logging daemon set, but a configuration error causes it to crash loop on startup. Because the daemon set's update strategy was misconfigured, it attempts to roll out to all nodes simultaneously, taking down logging and log-based security monitoring cluster-wide. How do you recover and secure the rollout strategy?
Answer: the rollout took down logging because the update strategy was configured with unrestricted concurrency. I would restore the monitoring pipeline using these steps. 1. Pause the rollout. Instantly update the daemon set's template configuration to a valid state, or change the update strategy to on delete to halt the automatic propagation. 2. Isolate the crashing nodes. Manually delete the crash looping pods on a few nodes to allow the control plane to recreate them using the corrected template. 3. Configure concurrency boundaries. Set the max unavailable parameter to a conservative value like 1 or 10% to restrict the upgrade blast radius. 4. Monitor rollout progress. Run standard rollout status checks on the daemon set to ensure the update propagates safely across the remaining nodes. Pro tip: tuning max unavailable is about balancing rollout velocity against risk. In large clusters, setting max unavailable to 10% or 20% speeds up deployment, but increases the blast radius of a bad configuration. If your daemon set manages critical path tasks like CNIs or security agents, keep max unavailable capped at 1. Here is Kubernetes configuration demonstrating how to configure a daemon set rolling update strategy to prevent cluster-wide monitoring outages. Disclaimer: always test code in a non-production environment. This code configures the update strategy to limit the rollout to one node at a time, ensuring a configuration failure is isolated before it can take down logging cluster-wide.
Production Incident 52. After rolling out a service mesh across your cluster, application teams report that their P99 network latency has spiked by 200 milliseconds. Your diagnostics show that the Envoy sidecar containers are hitting their hard CPU limits during peak traffic hours, causing severe CPU throttling on the network transit path. How do you resolve this sidecar starvation?
Answer: this is a proxy resource starvation issue. Sidecars run on the same network namespace as the main application container and handle all inbound and outbound handshakes, making them highly sensitive to CPU limits. To resolve the latency spike, I would audit our sidecar injection templates and increase the CPU requests and limits specifically for the Envoy container, avoiding bloated requests while guaranteeing enough headroom to handle connection peaks. I would also evaluate disabling sidecar injection for high-throughput, low-risk internal database traffic like REDs or local memcache connections by using namespace-level annotations, which bypasses the mesh transit path entirely and reduces the overall CPU load on the node. Pro tip: enforce explicit requests and limits specifically for sidecars. Starving a proxy of CPU can increase your P99 network latency across the entire service mesh, so it is safer to profile the overhead under synthetic peak load and avoid generic global templates that do not account for individual application traffic patterns.
Production Incident 53. During an auto-scaling surge, several critical pods fail to schedule, throwing forbidden, exceeded quota errors. You find that the namespace has a strict resource quota that restricts total memory requests to 10 GB, and the auto-scaler has hit this limit, blocking the application from handling the traffic surge. How do you resolve this quota blockage?
Answer: the autoscaler is blocked because the namespace's resource quota is exhausted. I would adjust the limits and restore scaling using these steps. 1. Audit active quota usage. Query the active resource quota usage in the namespace using kubectl to verify which specific resource limit has been exceeded. 2. Temporarily expand the quota. Apply an updated resource quota manifest with an expanded memory limit, for example, 20 GB to immediately unblock the pending pods. 3. Right-size existing workloads. Review the resource requests of running pods and scale down over provisioned deployments to reclaim quota space. 4. Enforce namespace limits. Implement a limit range in the namespace to automatically set sensible default requests for all new containers. Pro tip: resource quotas can easily block emergency hotfixes during an active incident. It is generally safer to define quotas with dynamic scopes or use a separate namespace for critical, auto-scaled system workloads to balance density versus headroom. Here is Kubernetes configuration demonstrating how to define resource quotas with scoped limits to prevent billing overruns without blocking critical workloads. Disclaimer: always test code in a non-production environment. This code defines the specific memory limits within the namespace, preventing workloads from over-provisioning host resources.
Production Incident 54. A platform engineer enables a strict pod security standard like restricted in a production namespace. Immediately, an existing, critical deployment fails to restart during a rolling update because its container spec does not meet the new security requirements, leaving the application with 0 running replicas. How do you resolve this deployment block?
Answer: this is a security policy enforcement block. The new pod security admission rules are rejecting the pod specs because the containers attempt to run with root privileges or lack required security context like run as non-root. True. To restore the application immediately, I would temporarily patch the namespace label to downgrade the pod security standard from enforce to audit or warn mode, allowing the pending pods to boot successfully while we update the manifests. Next, I would work with the application team to update their deployment spec, adding the required security context parameters like dropping capabilities and restricting root access before re-enabling the strict security enforcement on the namespace. Pro tip: avoid rolling out strict validating policies directly in enforce mode. Utilize dry run or audit modes to capture legacy workloads that violate standards, allowing you to remediate the configurations before enforcing the blocks.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 55. A custom controller is deleted from the cluster, but the custom resources it was managing are left in a terminating state permanently. The API server refuses to delete them because the resources still contain finalizers that were registered by the now deleted controller. How do you safely remove these stuck resources?
Answer: the resources are stuck because their finalizers cannot be resolved by the deleted controller. I would safely remove the blocks using these steps. 1. Inspect active finalizers. Query the stuck custom resource in YAML format using kubectl to locate the exact finalizers array in the metadata. 2. Audit external dependencies. Verify that any external resources like cloud load balancers or databases associated with the custom resource have been manually cleaned up. 3. Deploy a JSON metadata patch. Execute a targeted JSON patch command to strip the finalizer's array from the terminating resource. 4. Verify object deletion. Confirm that the API server immediately removes the resource from etcd once the finalizers are set to null. Pro tip: manually patching finalizers to null is a brute force escape hatch. If the controller that registered the finalizer is dead, removing it can lead to orphaned external resources like cloud load balancers or disks, so always verify the external state first. Here is bash code demonstrating how to safely remove finalizers from stuck resources using a JSON patch. Disclaimer: always test code in a non-production environment. This code removes all registered finalizers from the resource metadata, forcing the API server to delete the object immediately.
Production Incident 56. You attempt to delete a deprecated namespace, but the deletion hangs in a terminating state indefinitely. Running diagnostics reveals that several persistent volume claims PVCs inside the namespace are stuck, which in turn blocks the namespace controller. The PVCs cannot terminate because their underlying persistent volumes still contain the PVC protection finalizer, and the CSI node plugin is dead. How do you resolve this deadlock?
Answer: this is a storage to namespace deletion deadlock. The namespace controller is waiting for all resources to be deleted, but the PVCs are protected from removal because the API server believes they are still in active use by pods. To resolve this, I would first check the active pods on the node and verify that all containers mounting these volumes have been fully terminated. Next, I would investigate the CSI node driver logs to see if the storage system is hung on a physical unmount operation. If the host is safe and the physical disk is confirmed detached, I would manually patch the PVC objects to clear the Kubernetes.io or PVC protection finalizer, allowing the PVCs, the PVs, and ultimately the namespace to complete their deletion cycles. Pro tip: stuck PV or PVC terminations often point to a hung CSI node driver. Before modifying finalizers, inspect the CSI node registrar logs to ensure the storage system is not waiting on a physical detach that can block the node.
Production Incident 57. A platform engineer deletes a large development namespace containing thousands of resources, but the deletion remains stuck for over 4 hours. You find that the namespace controller is timing out on discovery sweeps because an unresponsive aggregated API service is failing to respond, preventing the controller from validating remaining custom objects. How do you unblock the namespace controller?
Answer: the namespace deletion is blocked because an unresponsive aggregated API service is causing the discovery sweeps to hang. I would unblock the controller using these steps. 1. Audit aggregated services. Query the active API services in the cluster to identify which specific aggregated API group is showing a false status. 2. Isolate the faulty endpoint. Filter the output to find API services that are timing out on health checks. 3. Temporarily remove the service. Delete the unresponsive API service object from the cluster to stop the API server from routing discovery requests to it. 4. Verify controller recovery. Once the blocked API service is removed, the namespace controller will complete its discovery sweep and finalize the deletion. Pro tip: stuck namespace deletions are typically blocked by failed aggregated API servers. Checking /API's discovery paths and temporarily removing blocked API services is often more reliable than trying to patch the namespace finalizers directly. Here is bash code demonstrating how to clean up a stuck namespace by bypassing unresponsive aggregated API services. Disclaimer: always test code in a non-production environment. This code queries all active aggregated API services, helping us pinpoint which third-party endpoints are timing out and stalling the namespace controller.
Production Incident 58. A custom database operator is deleted from the cluster, but because of a logic error in its controller code, it fails to execute its cleanup routines. It leaves behind dozens of orphaned cloud resources, like load balancers and block storage volumes in your AWS account, racking up thousands of dollars in hidden costs. How do you prevent and clean up these orphan resources?
Answer: This is an operator garbage collection failure. When custom controllers deploy external cloud infrastructure, they should register corresponding representation objects inside the cluster using proper dependency trees. To resolve the current leak, I would use our cloud monitoring tools to identify all untagged, orphaned load balancers and volumes associated with the deleted operator's namespace, and manually terminate them via the cloud CLI. To prevent future resource leaks, I would ensure that the operator's controller code registers native owner references on all child resources it creates. This leverages the Kubernetes garbage collection engine to automatically trigger cascading deletions of dependent resources when the parent custom object is removed. Pro tip: ensure your custom operators implement owner references on child resources. This leverages the native Kubernetes garbage collection engine to automatically clean up dependent objects when the parent resource is deleted.
Production Incident 59. A platform engineer deploys a high-priority batch data processing job. However, the job's priority class is misconfigured, and the scheduler begins aggressively evicting active, critical production microservices like your API gateway pods from the node pools to free up compute resources for the batch job, causing an immediate service outage. How do you restrict the preemption behavior?
Answer: the batch job is evicting critical pods because its priority class has an active preemption policy. I would configure safe scheduling limits using these steps. 1. Identify the priority class. Locate the specific priority class resource assigned to the aggressive batch job. 2. Soften preemption policies. Modify the priority class manifest, setting the preemption policy field to never. 3. Apply the updated policy. Apply the updated priority class to the cluster to change the scheduling behavior. 4. Reschedule evicted pods. The scheduler will now queue the batch pods for available resources rather than terminating running workloads. Pro tip: configure high-priority batch jobs with preemption policy. Never. This allows the pod to wait in the scheduling queue for resources rather than aggressively evicting running, lower-priority serving workloads. Here is Kubernetes configuration, demonstrating how to define a priority class with a non-preempting policy to protect production workloads. Disclaimer: always test code in a non-production environment. This code sets the preemption policy to never, letting the scheduler queue the pod instead of evicting active, lower-priority workloads.
Production Incident 60. A legacy logging pod writes massive unrotated standard out files to its local empty dir volume. Within hours, the node's local disk partition saturates, causing the kubelet to evict the pod due to ephemeral storage exhaustion, which takes down logging across the node. How do you resolve and prevent this storage eviction?
Answer: this is a local storage exhaustion eviction. When a container writes unrotated files or uses an unbounded empty dir volume, it can consume the host's shared disk space, forcing the kubelet to evict the pod to save the operating system. To resolve this immediately, I would clean up the node's local file systems and increase the container's log rotation frequency. To prevent future disk space evictions, I would configure explicit ephemeral storage resource requests and limits in the deployment manifest, and set a hard size limit on all empty dir volumes. This ensures the kubelet throttles or evicts only the rogue container when it exceeds its specific storage allocation, rather than waiting for the entire node's shared partition to run out of disk space. Pro tip: use ephemeral storage resource requests to let the scheduler handle local disk capacity. If pods write heavy unrotated standard out logs, the node's local disk can saturate, so write size based on observed peak logging velocity.
Category 3 Conclusion. Mastering pod and workload lifecycles.
Pod lifecycles are the active heartbeats of your applications. As we have seen in these 20 incidents, keeping workloads stable is not just about writing clean container code. It is about managing the orchestration loop. From configuring liveness probes that do not kill booting containers, to preventing sub-path config staleness, and resolving stateful volume locks after host crashes, the platform must coordinate these lifecycles with absolute precision. When you master these transitions, you ensure that application rollouts, autoscaling events, and failovers happen seamlessly without manual intervention or data loss.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Transition from Category 3 to Category 4.
But even the most perfectly scheduled, stable pod is useless if it cannot communicate with the rest of the cluster. If the pod lifecycles are the engines of your platform, then networking is the highways. When those highways fail, whether due to CNI tunnel MTU mismatches, core DNS socket overflows, or stale ingress keep alive timeouts, your services are left isolated and blind. We must now move from the workload lifecycle to the deep, high-performance packet routing of the cluster, Kubernetes networking incidents. Let's explore Category 4.
Category 4. Kubernetes networking incidents.
Networking in Kubernetes is a high-speed, multi-layered routing puzzle. In this category, we dive into the high-severity network failures that occur at the CNI, DNS, and proxy layers. From silent CNI packet drops and core DNS UDP socket overflows to gateway API route conflicts and asymmetric routing drops. We will test your ability to debug packet flows, optimize local caching, and keep low-latency network paths stable under heavy enterprise traffic.
Category 4. Kubernetes networking incidents 61 to 88.
Here are the 28 production incidents covering Kubernetes networking failures. Production Incident 61. Pod-to-pod communication failure across nodes CNI issues. Production Incident 62. Cluster DNS production failures, core DNS crashes, DNS latency, resolution failures. Production Incident 63. Core DNS upstream resolver saturation. Production Incident 64. Core DNS UDP socket buffer drops under heavy load. Production Incident 65. Node local DNS cache failures causing lookup timeouts. Production Incident 66. Kube proxy corruption breaking cluster IP communication. Production Incident 67. Service endpoints not updating correctly after pod restarts. Production Incident 68. Graceful shutdown or pre-stop hook race conditions causing intermittent 502 or 503 errors during rolling updates. Production Incident 69. Ingress keep alive timeout mismatches causing intermittent 502s. Production Incident 70. Gateway API route attachment conflicts blackholing traffic. Production Incident 71. TLS certificate expiration on ingress gateway. Production Incident 72. WebSocket or gRPC traffic failures through ingress. Production Incident 73. Load balancer health checks failing falsely. Production Incident 74. SNAT port exhaustion during high outbound traffic. Production Incident 75. MTU mismatch causing packet fragmentation issues. Production Incident 76. Asymmetric routing issues, for example, Linux RP_filter drops. Production Incident 77. IPv4 or IPv6 dual-stack CNI bugs breaking traffic. Production Incident 78. External traffic policy. Local misconfigurations causing severe load imbalance or dropping external traffic. Production Incident 79. Calico BGP peering failures or route advertisement leaks. Production Incident 80. Cilium eBPF networking instability or agent crashes. Production Incident 81. eBPF policy conflicts causing intermittent packet drops. Production Incident 82. VXLAN tunnel failures in Flannel. Production Incident 83. Network policy accidentally blocking production traffic. Production Incident 84. Cross-zone networking latency spikes. Production Incident 85. External API connectivity failure from cluster. Production Incident 86. Ingress-reload storms causing traffic disruption. Production Incident 87. Cloud firewall or security group misconfiguration blocking traffic. Production Incident 88. DDoS traffic overwhelming ingress infrastructure. Total 28 production incidents for Kubernetes networking. Let's start with Production Incident 61.
Production Incident 61. Pods on Node A can no longer communicate with pods on Node B across your cluster. Upon checking, you find that although local pod-to-pod pings work on the same host, cross-node packets are being silently dropped. The CNI logs indicate packet fragmentation on the virtual overlay network interfaces. How do you troubleshoot and fix this communication failure?
Answer: pods on different nodes cannot talk to each other because the CNI network interfaces have mismatched MTU sizes, causing packet fragmentation. I would resolve the routing drops using these steps. 1. Trace packet MTUs. Run a manual path MTU discovery ping between the nodes using the Do Not Fragment flag to identify where packets are breaking. 2. Check CNI interface specs, SSH into the nodes, and inspect the MTU sizes of the virtual Ethernet and tunnel interfaces using host networking tools. 3. Align MTU configurations. Update the CNI daemon set configuration such as Calico or Flannel config maps to scale down the CNI MTU size to accommodate the VXLAN or Genev encapsulation overhead. 4. Restart CNI pods. Perform a rolling restart on the CNI daemon set to apply the new MTU limits across all active node network interfaces. Pro tip: VPC and CNI tunnel encapsulation adds overhead to packets. If your CNI MTU matches the host MTU, packets will fragment and drop silently, so it is safer to scale the CNI MTU down to 1422 or 1450 to leave room for the VXLAN or Genev headers. Here is bash code demonstrating how to check virtual interface MTUs and perform path MTU discovery to find packet fragmentation limits. Disclaimer: always test code in a non-production environment. This code executes a ping with the Do Not Fragment flag set, helping us verify if the network tunnel can safely transmit 1450 byte packets without dropping them. Here is the code displaying all host network interfaces, allowing us to compare the physical interface MTU against the CNI tunnel MTU.
Production Incident 62. During a sudden traffic surge, internal service-to-service communication slows to a crawl, and several microservices begin throwing connection timeouts. You find that core DNS pods are crash looping due to memory limits, and the remaining instances are experiencing massive DNS resolution latency, paralyzing name resolution cluster-wide. How do you stabilize the DNS service?
Answer: core DNS is crash looping because its cache is misconfigured and overloaded. I would optimize the DNS routing using these steps. 1. Scale core DNS replicas. Scale up the core DNS deployment replica count to distribute the query load across more nodes. 2. Optimize core file cache. Edit the core DNS config map to adjust the cache sizes and enable prefetching for popular DNS records. 3. Tune core DNS memory limits. Update the core DNS deployment manifest to increase the memory limit, preventing kills during query spikes. 4. Implement autopath. Enable the autopath plugin in the core file to optimize multi-step search path resolutions and reduce upstream queries. Pro tip: default core DNS caches are often too small for high-traffic environments. Tuning the cache size and enabling prefetching in the core file can reduce upstream forwarding load by up to 40%. Here is Kubernetes configuration, demonstrating how to tune the core DNS core config map to optimize caching and prefetching. Disclaimer: always test code in a non-production environment. This code configures core DNS to cache successful and failed DNS resolutions, and enables prefetching to proactively refresh popular records before they expire.
Production Incident 63. Your primary microservice cluster experiences intermittent DNS timeouts when connecting to external third-party APIs. You discover that high-frequency external DNS queries from your application pods are bypassing the local core DNS cache and saturating your upstream network resolvers, causing silent packet drops on outbound requests. How do you protect the resolver limits?
Answer: this is an upstream resolver saturation issue caused by recursive search path expansion. When application pods make external lookups, they default to appending local cluster suffixes like .namespace.svc.cluster, .local if the domain name has fewer dots than the n dot setting in /etc/resolve.conf. This translates a single external DNS request into multiple sequential lookup attempts, which quickly saturates the upstream DNS resolver's rate limits and triggers silent packet drops. To resolve this, I would update our application deployment specs, setting DNS config.options to specify n.1. This forces the local resolver to query external domains directly as absolute names on the first attempt, bypassing core DNS search path expansion and instantly relieving upstream resolver load. Pro tip: upstream resolvers enforce strict rate limits per host node or network interface. If you see intermittent DNS timeouts, check your pod search path configurations in /etc/resolve.conf and optimize n-dots to prevent single external lookups from generating a storm of recursive queries.
Production Incident 64. During a heavy workload scale-up, your core DNS pods remain healthy and CPU usage is within limits, but application pods still report intermittent DNS lookup timeouts. Your host-level metrics show that the Linux kernel's UDP socket receive buffer for the core DNS process is overflowing, causing the operating system to silently drop DNS packets before the application can read them. How do you optimize the socket buffer?
Answer: DNS lookup requests are getting silently dropped because the Linux kernel's UDP buffer is overflowing under heavy traffic. I would tune the socket buffers using these steps. 1. Audit socket drops. Check the system's netstat logs on the core DNS nodes to verify if the UDP receive buffer errors are increasing. 2. Scale kernel max socket limits. Increase the kernel's maximum receive socket buffer limit using sysctl. 3. Adjust core DNS buffer allocations. Update the core DNS deployment manifest, injecting container-level settings to request larger UDP read buffers on startup. 4. Verify the buffer tuning. Run socket queries on the host to ensure the socket receive buffer size has successfully scaled to handle the incoming traffic. Pro tip: core DNS processes high-volume DNS requests over UDP, which does not have flow control. If you observe socket drop metrics increasing, scale the host kernel's RMM_max and configure core DNS to request larger buffer allocations. Here is bash configuration, demonstrating how to scale kernel UDP socket receive buffers to prevent packet drops under heavy DNS load. Disclaimer: always test code in a non-production environment. This code increases the kernel's maximum UDP read socket buffer size, allowing the operating system to queue incoming DNS packets during heavy traffic spikes without dropping them.
Production Incident 65. To reduce cluster-wide core DNS load, you deploy node local DNS cache on your worker nodes. However, immediately after deployment, several applications experience complete DNS lookup timeouts. You find that the local DNS caching agent is failing to bind to the local loopback IP address, causing all local DNS queries to hang. How do you resolve this local agent routing failure?
Answer: this is a local DNS routing loopback failure. Node local DNS cache runs a lightweight caching agent on each node, binding to a local IP, typically 169.254.20.10, and using IP tables rules to redirect DNS traffic. When lookups hang, the primary suspect is a systemd resolved conflict on port 53, a wrong bind IP configuration in the daemon set, or a host network port conflict with another system daemon. To resolve this, I would check the host's active listeners to verify no other service is binding to port 53 on the node's loopback. I would then inspect the node local DNS cache daemon set configuration and verify that the target IP table's redirection rules are successfully created on the host, ensuring traffic actually routes to the caching agent's listener. Pro tip: local DNS agents often conflict with system-level resolvers. When deploying node local DNS cache, always verify that systemd resolved or local DNSMask daemons are disabled or configured not to bind to the link local loopback IP, protecting port 53 on the host network.
Production Incident 66. After a worker node experiences a brief network disconnection, pods on that node can no longer connect to any internal cluster IP services. Your diagnostics show that, while direct pod-to-pod IP communication works, connecting via the service name or the cluster IP hangs. You suspect that the local kube proxy daemon has corrupted routing tables. How do you troubleshoot and fix this proxy failure?
Answer: this is a service routing sync failure. When a node experiences network instability, the local kube proxy daemon can fail to synchronize its IPVS or IP tables rules with the API server, leaving stale routing entries that prevent cluster IP traffic from reaching healthy endpoints. To resolve this, I would first inspect the logs of the local kube proxy pod on the affected node to find any synchronization or IP tables lock errors. Next, I would run host-level diagnostics to dump the active IPVS table, comparing the service routing entries against the actual backend pod IPs. To restore the routing immediately, I would execute a restart on the kube proxy pod, forcing it to resync and rewrite the host's networking rules cleanly from the API server. Pro tip: stale cluster IP routing is almost always a kube proxy sync failure. Running daily audits on local node IPVS tables can help identify nodes with out-of-sync services before they impact application traffic.
Production Incident 67. During a high-frequency microservice deployment, customers begin receiving intermittent connection reset errors. You find that when application pods are restarted, the active backend list is not updating quickly enough, causing the proxy and load balancers to route traffic to terminated pods. How do you identify the cause of the endpoint sync lag?
Answer: stale connection routing occurs because the endpoint sync pipeline cannot keep up with high-frequency pod deletions. I would troubleshoot the lag using these steps. 1. Audit pod termination behavior. Verify that application pods are handling SIGTERM correctly and completing their graceful shutdown sequence. 2. Validate readiness probes. Inspect the readiness probe configurations to ensure pods are not marked as healthy before they are ready to accept traffic. 3. Check controller backlog. Analyze the endpoint slice controller metrics to see if the queue backlog or sync latency is spiking. 4. Evaluate API server pressure. Monitor the API server's CPU and write latency to verify if high-frequency write operations are throttling the controller's updates. Pro tip: standard endpoints have scalability limits in large clusters. Utilizing endpoint slices reduces API server serialization overhead, but you should monitor the endpoint slice controller sync latency during mass scaling events. Here is bash code demonstrating how to inspect endpoint slices to audit the synchronization of service backend pods. Disclaimer: always test code in a non-production environment. This code retrieves all active endpoint slices associated with our payment service, helping us verify if the backend pod IP addresses match the active running pods.
Production Incident 68. During a rolling update of your core web application, your ingress controller begins logging a wave of intermittent 502 and 503 errors. Your investigation shows that the application pods receive the SIGTERM signal and shut down immediately, but the ingress controller still has the pod's IPs in its active endpoints list, routing traffic to dying containers. How do you prevent this race condition?
Answer: we are seeing intermittent 502 errors during rolling updates because the pods are shutting down before the ingress controller has time to remove their IPs from the active endpoints list. I would inject a graceful delay using these steps. 1. Locate the container spec. Open the application deployment manifest and navigate to the container lifecycle settings. 2. Inject a pre-stop hook. Configure a pre-stop lifecycle hook containing a sleep command to delay the container's shutdown. 3. Allow endpoint propagation. This delay gives the API server and the ingress controller several seconds to remove the pod IP from active routing tables. 4. Trigger the rolling update. Apply the updated manifest to ensure future pod terminations are executed gracefully without dropping active connections. Pro tip: a simple shell sleep command in a pre-stop hook is an effective way to handle the endpoint propagation lag. Setting a 5 to 10 second delay gives the ingress controller and load balancer enough time to remove the pod IP from active routes before the container receives sigterm. Here is Kubernetes configuration, demonstrating how to use a pre-stop lifecycle hook to prevent 502 or 503 errors during rolling updates. Disclaimer: always test code in a non-production environment. This code configures a pre-stop hook that forces the container to wait for 10 seconds upon receiving a deletion request, giving the ingress controller enough time to stop routing traffic to it before the main process is killed.
Production Incident 69. Your Nginx ingress controller is throwing intermittent 502 bad gateway errors under heavy, low concurrency traffic. You find that the ingress controller's keep alive timeout is configured to 60 seconds, while the backend node.js application's keep alive timeout is set to 5 seconds, causing Nginx to attempt to reuse connections that the application has already closed. How do you resolve this timeout mismatch?
Answer: this is a keep alive timeout mismatch. When the backend pod closes an idle TCP connection to save resources, but the Nginx ingress controller still believes the connection is active, Nginx will attempt to route the next incoming request down that closed socket, resulting in an immediate connection reset and a 502 bad gateway error. To resolve this, I would update the global Nginx ingress config map in the cluster, tuning the upstream keep-alive timeout parameter to 4 seconds. This ensures that the Nginx proxy actively terminates its idle connections to backend pods before the application runtimes can close them, eliminating the mismatch across the entire platform. Pro tip: keep alive timeouts must align across your ingress and backend application layers. To prevent intermittent connection reset errors, ensure your Nginx ingress keep alive timeout is slightly shorter than your application's connection timeout.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 70. 2 development teams deploy conflicting HTTP route resources targeting the same shared gateway API instance, using identical hostnames and paths, but routing to different backend services. The gateway controller enters a degraded state, and external traffic is blackholed. How do you resolve the routing conflict?
Answer: our routing is broken because two teams deployed conflicting HTTP route rules for the same domain, causing the gateway controller to drop the traffic. I would resolve the routing collision using these steps. 1. Audit active routes. Query the status of all active HTTP route resources associated with the primary gateway API controller. 2. Identify the conflict. Locate the conflicting route configurations that are targeting the duplicate hostname and paths. 3. Isolate the parent refs. Enforce strict parent reference rules in the gateway config, restricting which namespaces can attach routes to the shared gateway. 4. Apply namespace restrictions. Refactor the gateway listeners to utilize allowed routes to block unauthorized namespaces from claiming existing hostnames. Pro tip: gateway API controllers handle conflicts differently depending on the implementation. To prevent cross-namespace route hijacking, enforce strict namespace restrictions on your gateway listeners using allowed routes configurations. Here is Kubernetes configuration, demonstrating how to use the allowed routes directive in gateway API to restrict which namespaces can attach routing rules. Disclaimer: always test code in a non-production environment. This code configures the gateway to only accept route attachments from namespaces that have been explicitly labeled and validated, preventing unauthorized teams from hijacking routing paths.
Production Incident 71. The public SSL/TLS certificate on your primary ingress gateway expires, instantly dropping all external API connections and blocking customer checkout flows. Although a new certificate was purchased, the ingress pods are still serving the expired cert from their local cache. How do you recover and automate this renewal?
Answer: the gateway SSL cert expired, which immediately broke our external API connections. I would restore the TLS handshake and automate future renewals using these steps. 1. Deploy Cert Manager. Install Cert Manager in the cluster to manage the lifecycle of our Let's Encrypt certificates automatically. 2. Configure the issuer. Deploy a cluster issuer resource to handle the DNS01 or HTTP01 challenges with our cloud DNS provider. 3. Define the certificate resource. Create a certificate manifest that targets our ingress hostname and automates the certificate creation. 4. Verify secret updates. The ingress controller will automatically detect the updated secret and reload its config without dropping active connections. Pro tip: use Cert Manager to handle TLS renewals automatically. If you manage high-traffic ingress gateways, configure Prometheus to alert on the expiration metrics of the underlying secret rather than relying on external web pingers. Here is Kubernetes configuration, demonstrating how to use Cert Manager to automate TLS certificate creation and rotation. Disclaimer: always test code in a non-production environment. This code specifies the Kubernetes secret, where Cert Manager will write the renewed private key and certificate chain, which is automatically mounted by the ingress controller.
Production Incident 72. After deploying a real-time chat application, users complain that their connections drop every 60 seconds. You find that the WebSocket connections are being closed by your Nginx ingress controller because the proxy read and write timeouts are misconfigured, treating active WebSocket idle phases as dead connections. How do you stabilize the long-lived sockets?
Answer: WebSockets are dropping because Nginx is closing idle connections too quickly. By default, Nginx ingress has a 60-second read and write timeout, which is too aggressive for long-lived protocols like WebSockets or gRPC streams that have long periods of silence between messages. To resolve this, I would update our ingress resource annotations, scaling up both the proxy read timeout and proxy send timeout values to 3,600 seconds, which gives the sockets an hour of idle buffer. I would also ensure that the application itself implements lightweight ping-pong frames keep alives at the code level, keeping the connection active in the eyes of the routing proxy and preventing transit gateways from closing the socket. Pro tip: gRPC and WebSockets require long-lived TCP connections. To prevent proxies from dropping idle channels, ensure your ingress annotations specify long read and write timeouts and enable HTTP2 upstream.
Production Incident 73. Your cloud provider's external load balancer suddenly marks all your worker nodes as dead, taking down your entire ingress endpoint. The pods are completely healthy, but the load balancer is failing its health checks because of a mismatch in how the external target ports are mapped to the cluster's node ports. How do you restore the health check routing?
Answer: the load balancer is marking nodes as dead because of a health check port mismatch on the service. I would fix the target routing using these steps. 1. Identify the target port. Check the ingress service definition to find the exact port mapped for the load balancer's health checks. 2. Confirm node port registration. Ensure that the service's health check node port matches the port that the external load balancer is actively probing on the node. 3. Configure local health checks. Update the service manifest to specify an explicit health check node port alongside the external traffic policy. Local setting. 4. Verify balancer sync. Once the service port mapping is aligned, the load balancer will successfully reach the node's local proxy port and mark the targets healthy. Pro tip: when using external traffic policy, local, the cloud load balancer needs to probe a specific node-level health check port. Ensure this port is explicitly set and exposed in your service YAML to avoid non-standard auto-generated ports that can confuse external load balancers. Here is Kubernetes configuration, demonstrating how to configure a service with local health checking to prevent load balancer target drops. Disclaimer: always test code in a non-production environment. This code configures the service to only route traffic to nodes running active pods and sets a dedicated node port for the balancer's health checks.
Production Incident 74. During a heavy traffic surge, your payment processing workloads begin throwing connection timeout errors when making outbound API calls to external banking gateways. Your diagnostics show that your cloud NAT gateway is suffering from SNAT port exhaustion, dropping outbound packets because your nodes are spawning too many unique TCP connections. How do you resolve this network saturation?
Answer: this is a SNAT port exhaustion issue. When application pods make thousands of concurrent, short-lived outbound connections, they quickly consume the 64,000 available TCP ports on the cloud NAT gateway's assigned IP, causing new outbound packets to be silently dropped. To resolve this immediately, I would allocate additional static IP addresses to our cloud NAT gateway, which scales our total SNAT port pool by 64,000 ports per IP. For a long-term fix, I would refactor our application code to enforce strict TCP connection pooling reusing existing sockets rather than opening a new one for every API request, and configure local DNS caching to prevent redundant upstream lookups. Pro tip: if your workloads make thousands of outbound API calls, allocate multiple static IPs to your NAT gateway. This scales your total SNAT port pool, and you should enforce connection pooling inside your application runtimes.
Production Incident 75. Your cluster's application pods can communicate with small payloads, but as soon as a pod attempts to send a large database backup, the connection hangs and eventually times out. You find that the host operating system uses an MTU of 9,000 jumbo frames, but the virtual CNI overlay interface is configured with a standard MTU of 1,500, causing packets to fragment and drop silently during transit. How do you resolve this MTU mismatch?
Answer: this is an MTU mismatch issue. When the physical host is configured to send massive packets jumbo frames, but the virtual CNI network interfaces are capped at 1,500, any large data payload like a database backup or file upload will be fragmented incorrectly or dropped silently by the network switches. To resolve this, I would audit the CNI configuration such as Calico or Cilium and align the CNI MTU with the effective underlay MTU after accounting for encapsulation overhead like VXLAN or Genv headers. Once the configuration is updated, I would execute a rolling restart on the CNI pods to apply the new interface limits across all nodes. Pro tip: ensure your host and CNI MTU settings are aligned. Mismatches can cause large packets to drop silently while small packets succeed, making diagnostics highly confusing. Always calculate the encapsulation overhead of your overlay network before setting the CNI MTU.
Production Incident 76. After adding a secondary network interface to your worker nodes for database traffic, pod-to-pod routing across nodes fails. Packets are getting dropped at the OS layer because they arrived on one interface, but the kernel tried to send them out another, triggering strict RP_filter checks. How do you bypass the strict routing checks?
Answer: the host is dropping asymmetric traffic because strict reverse path filtering blocks packets that arrive on unexpected interfaces. I would configure sysctl to allow loose routing using these steps. 1. Audit active routing filters. Query the active kernel parameters on the host to check the state of the reverse path filtering configuration. 2. Soften the filtering rules. Edit the sysctl configurations to change the RP_filter parameter from strict mode 1 to loose mode 2. 3. Apply the changes globally. Save the sysctl configuration file and run the reload command to apply the loose routing rules immediately. 4. Verify packet transit. Test cross-node routing to ensure the host now accepts asymmetric traffic without dropping valid ingress packets. Pro tip: strict reverse path filtering can break complex multi-NIC container setups. Setting RP_filter to loose mode 2 allows the host to route asymmetric traffic safely without dropping valid ingress packets. Here is bash configuration demonstrating how to change sysctl parameters to use loose reverse path filtering to prevent asymmetric packet drops. Disclaimer: always test code in a non-production environment. This code configures the Linux kernel to use loose reverse path filtering, allowing the host to accept packets arriving on unexpected interfaces during complex multi-NIC operations.
Production Incident 77. You enable an IPv4 or IPv6 dual-stack configuration on your cluster to support modern clients. However, immediately after deployment, several application pods fail to communicate over the network. You find that the CNI is failing to allocate IPv6 addresses properly to the containers, and kubeproxy is throwing errors because it cannot build matching IPv6 IPvS routing tables. How do you troubleshoot and resolve this dual-stack failure?
Answer: this is a dual-stack allocation failure. Enabling IPv4 or IPv6 dual-stack requires coordinated support across your cloud provider's VPC CIDR ranges, the host kernel's IPv6 configuration, the CNI network allocator, and kubeproxy. To resolve this, I would first verify that the host nodes are receiving valid IPv6 prefixes from the cloud provider, and ensure that IPv6 packet forwarding is enabled in the host kernel. Next, I would inspect our CNI daemon set configuration like Calico or AWS VPC CNI to confirm that the IPAM IP Address Management plugin is configured to use dual stack mode and has an allocated IPv6 block. Finally, I would restart the kubeproxy pods to force them to build the necessary IPv6 IPvS rules for service endpoints. Pro tip: dual stack setups often fail because of stale IPv6 IP tables rules on older nodes. When migrating to dual stack, verify that your CNI is running a compatible container network version and that your cloud provider's VPC supports IPv6 CIDR allocations.
Production Incident 78. To preserve the original client IP addresses for security auditing, you set your ingress service config to external traffic policy. Local. Immediately, external traffic begins dropping intermittently, and some nodes are completely overloaded while others are idle. You find that because pods are unevenly spread, some nodes receive load balancer traffic but have no local pods running, resulting in dropped connections. How do you resolve this load imbalance?
Answer: using external traffic policy. Local keeps the client IP but can unbalance load balancer traffic if pods are unevenly spread. I would configure a local health check port and target balancing using these steps. 1. Assess pod distribution. Check the placement of your ingress controller pods to verify if they are distributed evenly across all active node pools. 2. Ensure even spreading. Implement pod anti-affinity or topology spread constraints to force even distribution of ingress pods across nodes and zones. 3. Consider daemon set deployment. Evaluate deploying the ingress controller as a daemon set if complete node-level coverage is required by your platform requirements. 4. Configure local health checks. Update the ingress service, specifying an explicit health check node port to let the load balancer probe node readiness. Pro tip: using external traffic policy. Local keeps the client IP but can unbalance load balancer traffic if pods are unevenly spread. If you use it, ensure you configure your cloud provider's load balancer to use a local health check target port to bypass empty nodes, or use pod anti-affinity to ensure even node coverage. Here is Kubernetes configuration, demonstrating how to configure a service with external traffic policy set to local to preserve client IPs safely. Disclaimer: always test code in a non-production environment. This code sets the external traffic policy to local, directing the cluster to preserve the original client IP address and avoid extra network hops across nodes.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 79. In your bare metal Kubernetes cluster, Calico's BGP peering fails with the top of rack TOR switch, taking down all external routing. To make matters worse, a route leak occurs, advertising private pod IP blocks directly to the corporate backbone and causing routing chaos across the entire enterprise network. How do you contain the BGP route leak and restore peering?
Answer: this is a BGP route advertisement failure. BGP peering is used in bare metal clusters to let the CNI advertise pod IP networks directly to physical network routers. If the peering fails, or if Calico's route filters are misconfigured, private pod IP blocks can leak to the corporate backbone, causing routing collisions. To contain the route leak immediately, I would configure strict BGP import route maps or prefix lists on our core physical routers to reject any incoming pod IP prefixes. Next, I would check the Calico BGP peer configuration to verify the AS numbers and MD5 authentication keys, and apply a strict BGP filter to ensure Calico only advertises specific, allowed IP ranges to the TOR switches, restoring secure peering. Pro tip: BGP route leaks can bring down your corporate network. Always configure your TOR switches and Calico BGP configurations with strict prefix lists to ensure private pod IP blocks are never advertised to external routing pools.
Production Incident 80. During a massive scaling spike, your Cilium CNI agent pods experience high CPU usage and begin dropping traffic, taking down local node routing. Your diagnostics show that Cilium is dropping packets because its underlying eBPF policy map has exhausted its hard-coded size limits, preventing the agent from compiling new connection tracking rules. How do you scale the eBPF map limits?
Answer: Cilium is dropping traffic because the eBPF policy map filled up during a scaling spike. I would scale the map limits using these steps. 1. Inspect active map sizes. Check the cilium agent logs to identify which specific BPF map, such as the connection tracking or policy map, has exhausted its size limit. 2. Scale the map limits. Update the cilium configuration, increasing the BPF map dynamic size ratio or explicitly scaling up the policy map limits. 3. Recompile the eBPF maps. Apply the updated cilium configuration to force the agent to regenerate the maps with expanded capacity. 4. Verify routing parity. Monitor the cilium agent status to ensure routing is stable and the policy map is no longer dropping connection requests. Pro tip: cilium maps are statically sized on startup. If you run large clusters with thousands of active network policies, scale the BPF map dynamic size ratio or increase policy map limits explicitly in the cilium Helm values to prevent map exhaustion drops. Here is Kubernetes configuration demonstrating how to tune the cilium CNI config map to scale eBPF map sizes and prevent connection drops. Disclaimer: always test code in a non-production environment. This code scales the maximum size of the eBPF policy and connection tracking maps, allowing cilium to track larger connection pools and apply network policies without dropping packets.
Production Incident 81. Following the deployment of a new security policy, several microservices experience intermittent, random packet drops. You discover that overlapping or contradictory cilium policies produce an unexpected effective policy outcome, resulting in traffic being denied despite administrators believing the traffic should be allowed. How do you troubleshoot and resolve this policy conflict?
Answer: this is an eBPF policy evaluation failure. When multiple cilium network policies target the same pod selectors but have overlapping, contradictory ingress or egress rules, the dynamic policy maps are evaluated in a way that can result in silent traffic denial. To resolve this, I would use the cilium CLI and cilium monitor tools directly on the node to track packet drops in real time, filtering for drops with a policy denied reason. Once the conflicting policies are identified, I would combine them into a single, unified policy that clearly defines allowed traffic, ensuring the controller can resolve the effective policy outcome cleanly. Pro tip: overlapping network policies can create non-deterministic evaluation outcomes. Use cilium policy validate in your pipelines to audit policy structures, and use Hubble to map and visualize service connections before enforcing new security rules in production.
Production Incident 82. Following a node OS patch event, pod-to-pod networking breaks completely between several nodes running the Flannel CNI. The logs indicate that VXLAN tunnel traffic is failing because the host firewall on the newly updated nodes is blocking UDP port 4789. How do you recover routing and optimize Flannel to bypass the VXLAN tunnel for local subnets?
Answer: the VXLAN tunnel failed because the host firewall blocked UDP port 4789. I would restore packet flow and optimize Flannel routing using these steps. 1. Open the firewall port. Update the host firewall rules such as UFW or firewalled on the nodes to explicitly allow inbound UDP port 4789 traffic. 2. Audit CNI configuration. Inspect the active Flannel config map to verify the network backend settings. 3. Enable direct routing. Modify the Flannel backend configuration to enable direct routing, directing nodes on the same L2 subnet to bypass VXLAN encapsulation. 4. Restart the Flannel pods. Perform a rolling restart on the Flannel daemon set to apply the direct routing optimization across all active nodes. Pro tip: VXLAN encapsulation adds packet overhead and CPU cycles. Enabling direct routing in your Flannel or Calico configurations allows nodes on the same physical subnet to route traffic directly via host routing tables, keeping VXLAN encapsulation active only for cross-subnet traffic. Here is Kubernetes configuration demonstrating how to configure Flannel to use direct routing to bypass VXLAN encapsulation on the same subnet. Disclaimer: always test code in a non-production environment. This code configures Flannel to route pod traffic directly through the host network interface, without VXLAN encapsulation, if the destination node is on the same local L2 subnet.
Production Incident 83. A security engineer deploys a strict network policy to isolate the database namespace. However, due to a missing namespace selector in the policy ingress rules, the policy accidentally blocks all legitimate production traffic to your main payment microservice, causing transaction failures. How do you quickly identify and fix the blocking policy?
Answer: legitimate traffic is blocked because a new network policy lacks proper namespace selector labels. I would locate and correct the policy using these steps. 1. Audit network policies. List all active network policies in the affected namespace to locate recently modified or deployed resources. 2. Identify block trailing logs. Check the CNI or service mesh logs on the node to verify if packets are dropping due to a specific policy block. 3. Inject namespace selectors. Update the blocking network policy, adding a specific namespace selector to allow traffic from the ingress or API gateway namespace. 4. Validate traffic flow. Apply the corrected network policy and monitor application connections to ensure the payment service is receiving packets. Pro tip: default deny network policies can easily take down production services if selectors are omitted. When deploying isolation rules, utilize a separate dry run namespace first, and verify that your policies explicitly include both pod selector and namespace selector to prevent wide-ranging routing drops. Here is Kubernetes configuration demonstrating how to configure a network policy with explicit namespace and pod selectors to prevent accidental traffic blocks. Disclaimer: always test code in a non-production environment. This code restricts the incoming network traffic, allowing packets only from pods running inside namespaces labeled as gateway infra.
Production Incident 84. After scaling your application across 3 availability zones, your P99 latency metrics show a significant increase. You find that your front-end pods in Zone US East 1A are frequently routing API calls to backend database replica pods located in Zone US East 1B, incurring high cross-zone latency and significant cloud network egress costs. How do you restrict routing to the local zone?
Answer: this is a cross-zone latency issue. By default, Kubernetes services balance traffic evenly across all endpoint pods regardless of their physical location, which leads to high cross-AZ routing and cloud bandwidth charges. To resolve this, I would enable topology-aware routing on our core service manifests by adding the service.kubernetes.io/topology mode. Auto annotation. This instructs the endpoint slice controller to group and prioritize endpoints by zone, ensuring that kubeproxy, or the local CNI, routes the frontend's API calls preferably to backend pods running in the same availability zone, reducing cross-AZ network hops. Pro tip: topology-aware routing significantly reduces network latency and cloud egress bills. Always check your Kubernetes version when applying this. In v1.27 and newer, use the service.kubernetes.io/topology mode. Auto annotation. Whereas in v1.26 and older, you must fall back to the legacy service.kubernetes.io/topology aware hints. Auto key to trigger the zone allocation logic.
Production Incident 85. Pods inside your payment processing namespace suddenly lose connectivity to external banking APIs. Running DNS queries inside the container succeeds, but attempting to curl the external API endpoints times out. How do you troubleshoot the egress path to identify where packets are being blocked?
Answer: this is an egress path failure. Since internal DNS resolution is working but TCP connections are timing out, the issue is likely a blocked firewall, a routing error at the NAT gateway, or an egress network policy constraint. To troubleshoot, I would first run a traceroute or use curl-i from a debugging container inside the same namespace to see if packets are leaving the node's local network interface. Next, I would inspect the active network policies in the namespace to verify if any newly deployed rules are blocking outbound traffic, or if an egress rule is missing the required external sitter blocks. Finally, I would check our cloud providers' egress security groups and NAT gateway metrics to ensure the outbound traffic is not being dropped at the cloud perimeter. Pro tip: egress network failures are common when security policies are enforced. Always configure egress network policies with a fallback rule that explicitly allows DNS lookups UDP or TCP port 53 to your cluster's core DNS service IP. Otherwise, your containers will not even be able to resolve external API hostnames.
Production Incident 86. In a large cluster with thousands of active routes, rapid microservice deployment updates cause the Nginx ingress controller to continuously reload its configuration. This reload storm spikes ingress CPU usage to 100% and drops active client keep alive connections, causing widespread downtime. How do you optimize Nginx to handle rapid routing updates?
Answer: the ingress controller is crashing because high-frequency reloads drop active TCP connections. I would stabilize the routing engine using these steps. 1. Audit ingress configs. Inspect the Nginx ingress controller config map to check the active reload and load balancing parameters. 2. Enable dynamic configuration. Configure Nginx to use Lua-based dynamic upstreams, which allows backend endpoints to update in memory without requiring a full configuration reload. 3. Tune the shutdown timeout. Increase the worker shutdown timeout to give old worker processes more time to drain existing connections during reloads. 4. Enforce rate-limited syncs. Adjust the controller's sync period annotations to batch rapid API updates together, reducing the frequency of configuration writes. Pro tip: Nginx ingress reloads are computationally expensive. Utilizing Lua-based backends like the default behavior in modern Nginx ingress controllers allows endpoint updates to occur dynamically in memory, reducing reloads by up to 90% and protecting active client keep alive connections. Here is Kubernetes configuration, demonstrating how to tune Nginx ingress config map parameters to prevent reload storms during rapid endpoint scaling. Disclaimer: always test code in a non-production environment. This code configures the worker shutdown timeout, giving old Nginx worker processes up to 4 minutes to gracefully drain active connection sockets during configuration reloads.
Production Incident 87. You provision a new node subnet in your cloud provider to scale out your cluster's compute capacity. However, the moment pods are scheduled on the new nodes, they fail to communicate with the rest of the cluster. You find that the cloud provider's security groups are misconfigured, blocking CNI VXLAN traffic UDP port 4789 between the old and new subnets. How do you resolve this cross-subnet firewall block?
Answer: this is a cloud-level security group block. Kubernetes CNI overlays like VXLAN or Genev rely on host-to-host UDP communication across specific ports to build the virtual container network. If your cloud provider's security groups or subnet routing tables do not explicitly permit this traffic between all node subnets, cross-node pod routing fails completely. To resolve this, I would access our cloud console and inspect the security groups assigned to the new worker nodes. I would add a security group rule that explicitly allows inbound and outbound UDP traffic on port 4789 for VXLAN and port 10250 for kubectl API communication between the subnets, instantly restoring cross-subnet cluster networking. Pro tip: security groups are often the silent cause of CNI routing failures during node scaling. When designing multi-subnet clusters, always configure a single, shared security group for all nodes that permits full inter-subnet communication on CNI ports, preventing manual firewall configuration errors during automated node scaling.
Production Incident 88. Your e-commerce API gateway experiences a sudden, coordinated distributed denial of service DDoS attack, flooding your Nginx ingress controller with millions of malicious HTTP requests. The ingress pods exhaust their available worker connections and crash, taking down all legitimate external traffic. How do you configure rate limiting to protect the ingress?
Answer: the ingress controller crashed because malicious client traffic exhausted the proxy connection pool. I would implement rate limiting protections using these steps. 1. Assess ingress annotations. Open the primary ingress resource specification to check if rate limiting or client connection limits are defined. 2. Enforce client IP rate limiting. Configure Nginx annotations to set a limit on the number of concurrent connections and requests allowed per client IP. 3. Set a burst buffer. Define a burst allowance parameter to let legitimate peak user traffic pass through without being dropped immediately. 4. Scale the ingress deployment. Increase the ingress controller's replica count and apply anti-affinity rules to distribute the network load across healthy node pools. Pro tip: basic ingress level rate limiting is a secondary defense. While configuring client IP limits in Nginx protects backend pods, a high-volume DDoS attack can still saturate your cloud provider's external load balancer. Implement a cloud-native web application firewall WAF or CDN at the edge to scrub malicious traffic before it reaches your ingress. Here is Kubernetes configuration, demonstrating how to use Nginx ingress annotations to enforce rate limiting and connection limits per client IP. Disclaimer: always test code in a non-production environment. This code configures Nginx to restrict each unique client IP address to a maximum of 20 concurrent connections and 15 requests per second, protecting downstream backend services from load saturation.
Category 4 Conclusion: Mastering Cluster Networking.
Kubernetes networking is a complex high-speed routing puzzle. As we have seen in these 28 incidents, keeping traffic flowing is not just about writing clean service specs, it is about managing the transport layer itself. From aligning host and CNI MTU sizes to prevent silent packet drops, to scaling core DNS UDP buffers, and configuring pre-stop hooks to eliminate 502 errors during updates, you must maintain absolute control over the packet path. By eliminating synchronization deadlocks, optimizing local DNS caches, and implementing strict traffic policies, you ensure that your services can communicate safely and efficiently under heavy, real-world traffic.
The universal interview tip: whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem: the search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Transition from Category 4 to Category 5.
But even if your network routing is perfectly fluid, stateless applications represent only half the story. If network highways are the veins of your cluster, then stateful storage is the memory. When stateful workloads boot up, whether they are distributed databases, cache engines, or file shares, they must attach to physical disks, mount file systems, and persist data safely across node failures. When storage drivers crash, volume attachments lock up, or IOPS limits are hit, your data engine stalls. We must now move from the virtual network layers to the physical and cloud storage fabrics. Storage and stateful platform incidents. Let's explore Category 5.
Category 5. Storage and Stateful Platform Incidents.
Storage is the most challenging boundary in cloud-native platforms because data has physical gravity. In this category, we dive into the high-severity failures that occur when managing persistent data, from stuck CSI volume attachments and multi-attach lockups to NFS stale file handles and IOPS throttling. We will test your ability to debug storage controllers, Safely manage volume lifecycles during upgrades, and protect database integrity when the underlying disk system fails.
Category 5. Storage and Stateful Platform Incidents 89 to 103.
Here are the 15 production incidents covering storage and stateful failures. Production Incident 89, PVC stuck in pending state. Production Incident 90, persistent volume mount timeout during deployments. Production Incident 91, CSI driver crashes causing storage outages. Production Incident 92, CSI controller stuck reconciling orphan volumes. Production Incident 93, CSI volume detachment timeouts during node drain holding up maintenance. Production Incident 94, EBS, EFS, Azure Disk, and GCE volume attachment conflicts multi-attach errors. Production Incident 95, NFS stale file handle and mount issues. Production Incident 96, empty dire file system quota exhaustion. Production Incident 97, iSCSI and multipath daemon failures on worker nodes. Production Incident 98, storage class misconfiguration preventing provisioning. Production Incident 99, storage IOPS and throughput throttling causing application degradation. Production Incident 100, volume expansion failure on stateful sets. Production Incident 101, read-write many storage contention causing latency spikes. Production Incident 102, volume snapshot and restore failures. Production Incident 103, backup corruption discovered during disaster recovery. Total 15 production incidents for storage and stateful platforms. Let's start with Production Incident 89.
Production Incident 89. A developer deploys a new database pod, but the persistent volume claim PVC remains stuck in a pending state indefinitely. Running diagnostics shows that the storage class is set to wait for the first consumer before provisioning the volume, but the pod cannot schedule because of restrictive node affinity rules, creating a deadlocked loop. How do you resolve the scheduling deadlock?
Answer: the pod is stuck waiting because the storage class is set to wait for the pod to schedule first, but the pod is blocked by a node selector. I would unblock the provisioning using these steps. 1. Identify the blocker. Run a describe query on the pending pod to verify if scheduling is blocked by CPU limits or node selectors. 2. Analyze the storage class. Inspect the storage class definition to check if the volume binding mode is set to wait for the consumer. 3. Soften node affinities. Modify the pod's node affinity or node selector rules to match the availability zones where storage is available. 4. Enforce immediate binding. If the storage engine supports it, transition the storage class to bind immediately, forcing the volume to provision first. Pro tip: using volume binding mode. Wait for first consumer is highly recommended for multi-zone clusters because it ensures the volume is created in the exact same zone where the pod actually schedules, preventing cross-zone storage mount failures. Here is Kubernetes configuration, demonstrating how to configure volume binding mode in a storage class to prevent scheduling deadlocks. Disclaimer: always test code in a non-production environment. This code configures the volume binding mode to delay provisioning until the scheduler has chosen a node, ensuring the storage is created in the same availability zone as the pod.
Production Incident 90. During a critical deployment scaling event, several database pods remain stuck in a container-creating state. The kubectl logs show that mounting the persistent volume PV is timing out continuously, and the node cannot establish a connection to the external NFS storage server, rendering the storage engine offline. How do you troubleshoot and unblock the mount?
Answer: this is an NFS mount timeout. While network firewall or security group misconfigurations are frequent causes, the timeout can also stem from DNS resolution failures, incorrect NFS export permissions on the storage server, route table misalignments, or an overloaded NFS server itself. To resolve this, I would first check the network path from the worker node to the NFS endpoint using tools like NC or Telnet on the target port, and verify that DNS resolves correctly from the node namespace. If the network is clear, I would audit the export policies on the NFS server to ensure the new node's subnet has authorized mount permissions, unblocking the mount handshake. Pro tip: NFS mount timeouts can have multiple root causes beyond simple firewall blocks. Always verify network connectivity. Check for NFS export permission mismatches and validate that the target storage server is not running out of available connection slots under high concurrency scaling spikes.
Production Incident 91. All storage-related operations, such as volume provisioning, attaching, and mounting fail cluster-wide, causing active deployments to freeze. You discover that the primary CSI driver daemon set pods have crashed on several nodes because they lost access to the local node's kubectl registration socket path. How do you recover the CSI driver health?
Answer: all storage mounts failed because the CSI driver pods crashed and stopped listening on the local Unix socket. I would restore the CSI registration using these steps. 1. Audit CSI daemon set logs. Query the logs of the crashing CSI driver pods to locate the specific socket connection or directory access errors. 2. Verify host directory paths. SSH into the worker nodes and verify that the local socket registration path exists and is accessible. 3. Clean up stale sockets. Delete any orphan Unix socket files in the registration directory to prevent binding conflicts. 4. Restart the daemon set. Perform a rolling restart on the CSI daemon set to force the pods to reinitialize and rebuild their API registration handshakes. Pro tip: CSI drivers rely on shared host directory paths to communicate with the local kubectl. If you upgrade your node operating system or kubectl version, verify that the host mount paths typically /var/lib/kubectl/plugins_registry remain unchanged to prevent daemon set crashes. Here is bash code demonstrating how to check the status of CSI driver daemon set pods and inspect their host level sockets. Disclaimer: always test code in a non-production environment. This code lists the files in the host's plugin registration path, allowing us to verify if the CSI socket files are present and have the correct permissions.
Production Incident 92. A cloud volume is manually deleted directly from your AWS console by mistake. The CSI controller in your cluster gets stuck in a permanent reconciliation loop, continuously trying to manage or delete the non-existent volume, which blocks subsequent dynamic provisioning requests in that namespace. How do you resolve this controller loop?
Answer: this is a CSI controller reconciliation loop caused by out-of-sync cloud storage metadata. Because the physical volume was deleted externally, but its representation volume attachment or persistent volume resource still exists inside the cluster, the CSI controller will continuously retry the detachment API calls, causing the provisioning queue to block. To resolve this, I would locate the stale volume attachment resource associated with the deleted disk and delete it using kubectl. If the deletion hangs, I would patch the metadata to clear out the finalizers, forcing the API server to remove the object immediately, which stops the controller's retry loop and unblocks the provisioning queue. Pro tip: never delete cloud storage volumes manually outside of Kubernetes. If you must clean up storage, always delete the PVC first. This allows the CSI driver to safely manage the physical volume deletion and keeps the cluster's internal state aligned with the cloud provider.
Production Incident 93. During a routine node drain for a rolling patch upgrade, the maintenance pipeline hangs for 20 minutes on a specific worker node. You discover that a block storage volume fails to detach from the host within the expected timeout period, holding up the automated upgrade. How do you bypass the detachment timeout?
Answer: the node drain is blocked because the cloud volume is stuck in an active detachment timeout phase. I would unblock the maintenance pipeline using these steps. 1. Verify mount status. SSH into the draining worker node and check the local mount directory to confirm the volume is no longer active in the host file system. 2. Check cloud provider state. Verify through the cloud provider console or CLI that the physical volume is shown as disconnected or safe to detach. 3. Force delete the API link. Once the physical state is verified, force delete the stuck volume attachment API resource to clear the logical cluster side lock. 4. Force detach via cloud CLI. If the volume is still stuck in the cloud control plane, execute a manual force detach command via the cloud CLI. Pro tip: force deleting the volume attachment resource is a high-risk operation that can lead to split brain or volume corruption if done prematurely. Only execute the force deletion after verifying the volume is no longer mounted on the host file system and the cloud provider confirms the physical detachment state. Here is bash code demonstrating how to locate and force delete a stuck volume attachment to unblock a node drain. Disclaimer: always test code in a non-production environment. This code force deletes the stuck volume attachment object, telling the controller manager to stop waiting for the cloud API to detach the volume and letting the node drain finish.
Production Incident 94. During a deployment rolling update, the new database pod gets stuck in a container creating state, and the events show multi-attach error for volume errors. You find that because the volume uses a read-write-once storage class, the new pod cannot mount the disk, because the old pod on another node has not released the storage lock yet. How do you resolve this rollout block?
Answer: the deployment rollout is stuck because the old pod has not released the volume, and the new pod cannot mount it because of the read-write-once limit. Read-write-once RWO storage can only be attached to a single host node at a time. During a rolling update, the scheduler may place the new pod on a different node, but the volume is still attached to the old pod's node, creating a lockup. To resolve this immediately, I would patch the deployment spec to change the strategy .type from rolling update to recreate. This forces the old pod to terminate and release the volume lock first, allowing the new pod to successfully mount the disk and start up on its node. Pro tip: using strategy. Rolling update for RWO volumes is a common cause of rollout hangs. If your stateful workloads use block storage that cannot be attached to multiple nodes, always use recreate strategy to ensure the volume is released before the new pod attempts to mount it.
Production Incident 95. Your shared NFS storage server experiences a brief network disconnection. When the server comes back online, all application pods mounting the shared NFS directory begin throwing stale file handle errors, and all read and write operations fail, paralyzing file processing. How do you recover the stale mounts?
Answer: the pods are throwing stale file errors because the NFS server's reboot broke the active TCP connection sockets. I would force recover the mounts using these steps. 1. Identify the dead mounts. SSH into the worker nodes and run mount checks to locate the specific stale NFS directory paths. 2. Execute a lazy force unmount. Run a lazy forced unmount command on the stale path to release the hung system handles. 3. Force delete the stuck pods. Delete the application pods using kubectl to force the kubelet to re-initialize the container mounts. 4. Verify mount recovery. Check the container logs to ensure the new pods have successfully re-established clean mounts to the NFS server. Pro tip: stale file handle errors cannot be recovered in place. The host kernel's network socket must be unmounted and re-established. Always use the lazy unmount umount-f-l command to cleanly release the dead socket without hanging your terminal. Here is bash code demonstrating how to execute a lazy force unmount on a stale NFS mount path on a worker node. Disclaimer: always test code in a non-production environment. This code executes a lazy and forced unmount, instantly releasing the stale mount handle from the node's memory without waiting for the unresponsive NFS network socket to close.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 96. A developer deploys an application that writes heavy temporary debug data to its local empty dir volume. Within hours, the pod is evicted by the kubelet with ephemeral storage limit exceeded reasons, but because the pod has no resources limit set, the unrotated data fills the shared node file system, crashing the node. How do you restrict empty dir limits?
Answer: the pod's temporary data filled the shared node disk because the empty dir volume was unbounded. When you mount an empty dir volume, it shares the node's local storage partition. If a container writes data without a limit, it can easily saturate the shared disk and take down the host operating system. To resolve this, I would update the pod's manifest, adding a hard size limit parameter to the empty dir volume configuration. This ensures that if the container's temporary writes exceed the limit, the kubelet will immediately evict only the rogue container, protecting the host's shared disk space from saturation. Pro tip: unbounded empty dir volumes are a massive host-level security risk. Always enforce a global limit range, or use a policy engine like Kyverno to ensure that every empty dir volume has a strict size limit defined to protect node disk space from silent exhaustion.
Production Incident 97. In your bare metal cluster, several high-throughput block storage volumes disconnect suddenly. Upon checking, you discover that the host's multipath daemon has crashed, causing the operating system to lose its redundant I/O paths to the storage array and dropping active container writes. How do you recover the storage daemon?
Answer: the storage path disconnected because the host's multipath daemon crashed, breaking the redundant connection paths. I would restore the storage paths using these steps. 1. Check daemon status. SSH into the worker node and run a status query to verify if the multipath service is stopped or frozen. 2. Restart the multipath service. Use systemctl to restart the multipath daemon and check the system logs for error details. 3. Verify active storage paths. Run diagnostic commands to list all active block storage paths and ensure redundant connections are restored. 4. Force kubelet rescan. If the volumes still show disconnected, trigger a storage scan on the node to force the kubelet to redetect the paths. Pro tip: multipath failures are common in bare metal environments using iSCSI or Fiber Channel. Always configure multipath with automatic path monitoring and failback policies to ensure the host can survive a network port drop without taking down your container storage. Here is Bash configuration, demonstrating how to check the status of multipath storage paths and restart the host daemon. Disclaimer: always test code in a non-production environment. This code lists all active redundant storage paths, allowing us to verify if the disk connections are healthy and have successfully re-established paths to the storage array.
Production Incident 98. A platform team deploys a new storage-backed application, but all PVCs remain in a pending state. The logs show that the storage class references a non-existent cloud provisioner name and uses a KMS key that the cluster's CSI driver does not have IAM permissions to decrypt, blocking dynamic provisioning. How do you correct the storage class configuration?
Answer: the storage provisioning failed because the storage class is misconfigured and the CSI driver lacks decrypt permissions. If the storage class points to an invalid provisioner name, or if the KMS key used to encrypt the volumes is not permitted in your CSI driver's IAM role, the Cloud API will reject the provisioning requests. To resolve this, I would edit the storage class definition, correcting the provisioner name such as ebs.csi.aws.com, and verifying that the KMS key ARN is spelled correctly. I would then update our cloud provider's IAM policy, explicitly granting the CSI driver's IAM service account role permission to use that KMS key for decrypt and encrypt operations, unblocking the dynamic provisioning queue. Pro tip: While some fields like reclaim policy can be modified in place, many storage class parameters cannot be safely changed after volumes have been provisioned. If you must modify a fundamental parameter like the encryption key, it is safer to create a new storage class, update your workloads to target the new resource, and migrate existing data sequentially.
Production Incident 99. Your high-throughput transaction database begins experiencing severe latency spikes. Your diagnostics show that the database pods are experiencing extreme I/O wait times because they have exhausted the baseline IOPS limit of their cloud volume, causing the cloud provider to throttle disk performance. How do you scale the storage performance?
Answer: the database is degraded because it has hit its baseline IOPS limits. I would scale the performance based on the specific cloud volume type. 1. Determine volume class. Check the storage class definition to see if the volume is provisioned as GP2, GP3, or an IOPS-optimized class. 2. Scale GP2 via size. For older GP2 volumes, patch the PVC to increase the capacity request, which dynamically scales baseline IOPS historically 3 IOPS per GB. 3. Tune GP3 via provision limits. For GP3 volumes, update the storage class or PVC to explicitly request higher provision IOPS and throughput independent of storage size. 4. Trigger volume update. Apply the updated manifest to trigger an online volume modification through the cloud provider's storage controller API. Pro tip: understand your storage type's scaling behavior. Older GP2 volumes scale performance linearly with size, making a larger disk the only way to get more IOPS. Modern GP3 volumes allow you to scale throughput and IOPS independently of disk size, letting you right-size costs without over-provisioning storage capacity. Here is Kubernetes configuration, demonstrating how to configure provisioned IOPS and throughput in a GP3 storage class to prevent storage throttling. Disclaimer: always test code in a non-production environment. This code configures the storage class to provision 6,000 IOPS and 250 megabytes per second of baseline throughput, ensuring high-throughput databases are not throttled by the cloud provider.
Production Incident 100. A platform engineer increases the storage request size in a stateful set's persistent volume claim, but the volume expansion fails to propagate to the running containers. The events show that the CSI driver does not support online volume expansion, or the underlying host file system like XFS is locked in a read-only state due to disk errors, blocking the resize. How do you resolve this expansion failure?
Answer: the volume expansion failed because of a storage driver limitation or a local file system error. Online volume expansion can easily fail if the CSI driver does not support live resizes, if the file system has fallen into a read-only state due to underlying I/O errors, or if there is a node side resize failure. To resolve this, I would check the storage class to ensure allow volume expansion. True is enabled, and inspect the node's DMESG logs for any read-only disk state errors. If the file system is healthy but the CSI driver requires offline expansion, I would temporarily scale down the stateful set replicas to 0, allowing the cloud provider to safely expand the disk while unmounted before scaling the database back up. Pro tip: volume expansion is a two-step process. The cloud provider resizes the physical block device, and then the node-side CSI driver resizes the partition file system. If the second step fails, check the node's kubectl logs to ensure it is not hanging on the resize command, which can occur if the local file system has read-only or mount lock errors.
Production Incident 101. Multiple application pods are configured with a read-write many RWX volume using AWS EFS to share static configuration files. During peak traffic hours, all pods experience massive latency spikes when reading the directory. You find that high concurrency file writes are causing heavy metadata lock contention, saturating the EFS throughput. How do you optimize the mount performance?
Answer: the shared storage is experiencing latency spikes because high concurrency writes are saturating the EFS throughput. I would optimize the mount options using these steps. 1. Locate the PV definition. Open the persistent volume PV manifest associated with the shared EFS storage. 2. Optimize mount parameters. Modify the mount options array in the PV, injecting tune parameters like R size, W size, and no time. 3. Bypass metadata updates. Setting no time stops the storage system from updating the file access timestamps for every read, reducing metadata overhead by up to 30%. 4. Restart the pods. Recreate the application pods to force the nodes to mount the shared storage using the new optimized TCP parameters. Pro tip: shared file systems like EFS or NFS struggle with high concurrency metadata updates. Always mount your RWX volumes with no time and not time to stop the storage engine from writing access time metadata for every single file read, which significantly reduces network traffic. Here is Kubernetes configuration, demonstrating how to configure high-performance mount options in a persistent volume to optimize NFS or EFS throughput. Disclaimer: always test code in a non-production environment. This code defines the specific TCP mount options for the NFS client, optimizing read and write buffers to 1 MB, and disabling access time updates to reduce network metadata overhead.
Production Incident 102. You attempt to restore a critical database volume from a volume snapshot during an incident, but the restore process fails. The events show that the volume snapshot class lacks the correct driver name, or the cloud provider API limits are exceeded during the snapshot creation, leaving you with empty, unusable backup files. How do you troubleshoot the snapshot controller?
Answer: the volume restore failed because the snapshot class is misconfigured or has hit cloud provider limits. If your volume snapshot class specifies an incorrect driver name, the volume snapshot controller will not be able to communicate with the cloud API. To resolve this, I would first inspect the volume snapshot and volume snapshot content resources to check if they have successfully reached a ready status. If the status is false, I would evaluate the logs of the cluster's external snapshot or controller pods to see if there are any API authentication or rate-limiting errors. Finally, I would verify that our cloud provider's IAM roles grant the controller the required permissions to take snapshots and create volumes from them. Pro tip: volume snapshots are not instantly consistent. Before trusting your snapshots for disaster recovery, always verify that the underlying volume snapshot content object has ready to use, true set, and configure validation scripts to test a restore in a staging environment.
Production Incident 103. During a disaster recovery drill, you restore your primary database from an automated Velero snapshot, but the database engine fails to start due to table corruption. You find that Velero took the snapshot of the active live database while it was undergoing heavy write operations, resulting in a crash-inconsistent, corrupted backup. How do you configure consistent snapshots?
Answer: the restored backup was corrupted because Velero took the snapshot while the database was actively writing data. I would configure pre-backup and post-backup hooks to flush the cache using these steps. 1. Access the pod spec. Open the database deployment or stateful set manifest and locate the metadata annotations. 2. Configure pre-backup hooks. Add annotations that instruct Velero to execute a database flush and read lock command before the snapshot is taken. 3. Configure post-backup hooks. Add corresponding annotations that instruct Velero to release the table lock once the snapshot is completed. 4. Verify consistent backups. Run a test backup with the hooks active, ensuring the database tables are cleanly locked and unlocked to guarantee a crash-consistent state. Pro tip: taking snapshots of active databases without locking them is a major risk. Always use Velero pre-backup and post-backup hooks to run a flushing read lock on your database engines before the storage volume is snapshot, ensuring transactional consistency. Here is Kubernetes configuration, demonstrating how to use Velero hook annotations on a pod to flush and lock a database during snapshot operations. Disclaimer: always test code in a non-production environment. This code configures Velero's pre-backup hook, instructing the backup runner to execute a flushing read lock on the database engine immediately before the storage volume snapshot is initiated.
Category 5 Conclusion. Mastering stateful storage and CSI drivers.
Storage is the hardest part of running Kubernetes because you cannot just throw away data when things break. As we have seen in these 15 incidents, stateful stability is about managing the precise lifecycle of physical and cloud block storage. When a node crashes, you must know how to safely force detach stuck volumes without causing data corruption, Configure your storage classes to scale IOPS correctly, and use database consistent backup hooks to protect your backups. By mastering the storage fabric and your CSI drivers, you ensure that even during sudden physical failures, your data remains safe and your stateful workloads can recover automatically.
Part 1 Conclusion. The core infrastructure is secured.
We have completed our deep dive into the core infrastructure of the Kubernetes platform. Across these first 103 production incidents, we have covered the absolute boundaries of the cluster itself. We have mastered control plane stability, host operating system constraints, pod lifecycles, high-performance networking, and stateful storage. You now have the forensic skills to identify, isolate, and recover from any failure that occurs within the baseline execution layers of the cluster.
Transition from Part 1 to Part 2. From core to scale.
But having a stable, running cluster is only the starting point. When you run Kubernetes in a massive, multi-tenant enterprise environment, the biggest challenges often come from the scale itself. The tools you use to manage, automate, and secure your cluster, like GitOps pipelines, autoscalers, monitoring agents, and identity providers, can become your greatest failure points when pushed to the limit. To reach the staff level, you must understand what happens when these advanced platforms break under load.
Part 2. Enterprise operations, scale, and security nightmares.
Having a running cluster is only 20% of the job. In Part 2, we are exposing the scale-breaking platform incidents, from GitOps sync storms wiping workloads, to autoscaler thrashing, telemetry crashes, and SSO failures. We will dive into the operational reality of running hundreds of clusters across multi-cloud environments, ensuring you can design and protect the platforms that run modern enterprise operations.
Part 2. The Enterprise Frontier Production Incidents, 104 to 218.
In the second video of this masterclass series, we will cover the final 115 incidents across these 9 critical operational domains. Category 6. Deployment, GitOps and Release Incidents Production Incidents 104 to 120. Category 7. Autoscaling, Capacity and Traffic Incidents Production Incidents 121 to 133. Category 8. Observability and Monitoring Incidents Production Incidents 134 to 149. Category 9. Security and Governance Incidents Production Incidents 150 to 168. Category 10. Cloud Kubernetes Platform Incidents Production Incidents 169 to 184. Category 11. Service Mesh and Advanced Traffic Incidents Production Incidents 185 to 191. Category 12. Platform Tooling, IDPs and CI and CD Production Incidents 192 to 201. Category 13. Disaster Recovery and Multi-Cluster Incidents Production Incidents 202 to 209. Category 14. High-Scale Reliability and Platform Failure Incidents Production Incidents 210 to 218. 115 high-stakes scenarios remain to complete your mastery of the Kubernetes ecosystem.
Complete the series. Part 2 is waiting.
Your journey to mastering Kubernetes platform engineering is only halfway complete. To dive into the final 115 real-world incidents, covering GitOps collapses, Carpenter scaling loops, Prometheus memory crashes, and multi-cluster disaster recovery, go directly to the video description below. You will find the link to Part 2, where we will complete your transition to a high-scale infrastructure specialist. See you in the next video.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
For more exciting tips, tricks, and more importantly, for valuable insights of interviews, please share, like, and subscribe to my channel. It has a lot of valuable information about various insights of interviews. It has a wide range of real-world portfolio projects of various technologies for interviews, and it has wide range of most asked interview questions and answers of various technologies like data science, SAP, AWS, DevOps, and full-stack web development, and more. That will be useful during interviews. It has a wide range of most asked interview questions and answers and real-world portfolio projects of various technologies for freshers, for 2 to 3 years, experienced candidates, and for 5 or above years, experienced candidates to test their skills by knowing most asked interview questions and make themselves ready for interviews.